right, good afternoon, everyone. Hope you had a good weekend. So first things first, we have a test on Thursday. So talk a little bit about that towards the end of class. I just sent out the solutions to at least the first exam review. Then there were a few problems on the second exam review that we need to talk about. I'll do that in class. And then what else? Oh, the quiz was due well, it's due now at 1 o'clock today. The one that I gave at end of class last time. So I checked, I think there were 17 students submitted the quiz. So I'm gonna close that out now. And I'll get to those when I have a chance. Are there any questions before I begin? We're all good, we're happy?
Just for the test on Thursday, we can only have the 6 formula pages that you showed us at the beginning.
And I'll let you have that limit summary that I provided to all of you. That has the, you know which one I'm talking about?
Right, like the 4, it's like the 4 quadrants, but yeah.
Yeah, that
And it has to be printed out though, because our computer screens have to be off, correct?
have to be, yeah, these have to be printed out. Okay, all right, so I was gonna jump right into chain rule today, but I decided with some of the
sir, I'm not sure if I can hear you.
I'm sorry?
I'm not sure if I can hear you.
You can't hear me? Can everyone else hear me?
Sound all right on my end.
Okay, it might be you, Alejandro. You might want to log out, log back in. I'm not sure.
Oh, there we go.
You good? Okay.
Yeah.
All right, so before I begin today's very, very important topic, which will not be on the test, okay? The topic we covered today will not be covered on the test. Before I get into that, I just want to kind of, because of some of the questions I got on the quiz question, I just want to remind you that the main idea kind of what we've learned, and that is, if somebody gives you a function, y equals some function of x, and from that we want to find the equation of the tangent line, then what we do is we use the point slope formula for a line, which is, this is the standard formula for the equation of the line. If we know a point on the line and the slope. Oh, sorry. You're given not only the function, sorry, you're also given x equals, you know, some number, whatever. So if we want to know the equation of the tangent line to that curve at that x value, whatever it is, then you have to just be able to fill out this formula. So there are a few things that are easy. This right here is just the number you're given, okay? That's always the x coordinate, the x1. And the y1 is always just going to be the point on this curve. So all you do is take your function and plug that number that you were given into it. That'll be your y1. The calculus comes in trying to find the slope of the tangent line, and that's where you take the derivative of the function and plug that number into that derivative. That's the basic idea. The question becomes, how complicated can we make these functions, right? The more complicated they are, the harder it is to take their derivatives. And that's why we're learning all these rules, okay? So that's just the general idea of how you find the equation of a tangent line to a function or to a curve. All right, so today is the chain rule, all right? So the chain rule is by far the most important rule for taking derivatives. It's the hardest for most students. And in order to do chain rule, you have to be comfortable with all the rules we've done already. So at this point, I expect that you've had a whole weekend to make sure that you understand the power rule, the product rule, and the quotient rule. And with that, you know, with that knowledge now, we move to the chain rule. So what makes the chain rule difficult is that it goes back to a topic in college algebra called composition. So I'm going to remind you first, before we get to the rule, what composition of two functions is. So I will provide these to you, these notes that I'm writing. I'll post these on Canvas. Did I do that last time? Hold on. I thought I did it. Let me just check our class. Something tells me I did do this and I forgot to tell you all. Maybe I didn't. Okay, well, what I'll do is later today, I will post PDF copies of all the notes that I've done in class. So everything I'm writing down, I'll make a PDF version of it and I'll send it to you so you have it. So don't focus too much right now about copying everything down. And you always have the video you can go back and watch, okay? All right, so in college algebra, if you're given two functions of x, let's call them f and g, and I color coded them for us here. F is the red function, G is the green function. If you're given two functions, then we have this thing called composition. It's an operation between the two functions. It's not multiplication, it's not division, it's not addition, it's not subtraction, it's composition. And what it is, this is the notation we use for it, f of g of x. And that you may have heard in college algebra calling it fog or something like that. It's f of g of x. And what it means is that you're going to take the f function and you're going to plug into it the g function. So the g function here is what I'm going to refer to as the inner function, and the f function is the outer function. So this is all just notation and language. Let's look at a specific example. We're not talking about derivatives yet, okay? So as a specific example, let's say I give you a function, this is example one. Say I give you a function f of x is sine of x, okay? So that's our red function. And g of x is x cubed. And I ask you to find f of g of x. Then that means you're going to take the f, treat it like the outer function, and take the g and put it inside the f function. So what we can do is we can just replace the g with what it is, right? G of x is x cubed. So we just replace this green with what it is. And then what we still need to do now is evaluate f at that input. So now we're going to take x cubed and plug it into the sine function and replace that x right there with the x cubed. So I'm going to take the sine and plug that g into that sine function. And that results in this final result, sine of x cubed. Does that all look familiar to you? Yes? Okay. So if we look at this right here, our final result, this final result, let's say that I didn't tell you anything, okay, and we just forget everything I just said, okay, and I tell you, hey everyone, I've got this function y equals sine of x cubed. The question and what's going to be the challenge for you with the chain rule is, can you look at that function and see that it is the composition of two functions? So go backwards from where we just came. So can everyone see that this is an inner function and this is an outer function? And therefore I can call the outer function f and call it the sine function. And I can call the inner function g and let that be x cubed. And then if I do that, then I can say that this is the same as f of g of x. Right? Any questions on that? We're going to look at another one now, if there's no questions. And what all I'm going to do is I'm going to switch them around. Okay? So what if I started everything out and said, hey, everyone, f of x is x cubed instead of sine x, and the g of x is the sine x. Then if we're asked to do the composition f of g of x, you'll still have an outer function and an inner function, but they've now interchanged places, haven't they? And so what you're going to do is take the outer function f, inside of it, you're going to put the g function, which in this case is sine of x, and then evaluate the f function at sine. So you're going to replace the x in the f function with the sine of x, which means you're just going to cube it. And then of course, sine of x cubed is the same as writing sine with a cubed and then the x. That's just notation. It's another, these are equivalent expressions. Okay. So that, again, that's just college algebra. But what we want to be able to do today is say, hey, look, what if I give you sine cubed x and I ask you to break it down into an inner and an outer function? Are you going to be able to look at that and see the inner and outer? So I think you might have to, I guess, well, we're, since we're just beginning this, you might have to rewrite it the other way first. And that way you can see what the inner one is. And the outer one's a little harder to see here because the outer one is this cube thing, right? The cubed is the outer. So we'll call the outer one F. It's what it does is cubes things. And the inner one, well, that's the G, and that'll be the sine X. Again, we have not looked at how to take a derivative or anything right now. We're just making sure we understand how this composition works. Questions?
Just so I was thinking of maybe making a connection. So is like the derivative of tangent then going to be considered a composition because it's secant squared of x? Or no, is that just something else? I just was thinking.
Yeah, no. The derivative of tangent of x being secant squared of x, we didn't talk about this. I gave that to you. Remember I gave that to you? I just told you.
Right, you did.
Yeah. But the way you could convince yourself is you could first, if I want to know derivative of tangent, I could rewrite tangent as sine over cosine. Couldn't I?
Good.
Okay, now this is not composition. This is just quotient, right? And so if I took the derivative of this, I would do the quotient rule, which would be the derivative of the top. So I need to take derivative sine of x times the bottom function minus the derivative of the bottom function times the top function all over the bottom squared, right? That's what quotient rule will get you. And then on top, I still need to take derivatives. So derivative of sine of x is cosine of x times cosine of x minus, now the derivative of cosine of x is negative sine x times sine x all over cosine squared x. And look at what the numerator turns into. Cosine squared x, that's these two multiplied together, minus minus is plus sine squared x over cosine squared x. And what's cosine squared x plus sine squared x on top? It's a Pythagorean identity.
1.
1. So this is 1 over cosine squared x. But 1 over cosine is secant. So this is actually just secant squared x.
Okay.
So I didn't do it, but you can prove that the derivative of tangent of x is now secant squared of x, but it only requires that you understand the quotient rule. So it is not composition. It's not part of the chain rule. Okay. Now let's do another example, because I really got to make sure you understand this. Okay, let me take this to a different page. Okay, so I'll go a little faster through this. We have two functions, f of x equals the square root of x. And g of x is this rational function. So if we're asked to find f of g of x, you're going to take the outer function to be f, the inner function to be g. First, you start by replacing this with g. So replace the g of x with the expression. And then you still have to plug all of that into f. And all f does is takes the square root. So we're just going to take the square root of all that. And that's your answer. Okay? That's it right there. But again, the question today is, if I give you this, can you take that and break that down into an inner and an outer function, right? Can you see the inner function is that x plus 1 over x minus 3, and can you see that the outer function is the square root function? That's going to be the challenge for you, is to be able to identify the inner and the outer. And as you do more problems, I think you get better at it, okay? All right, y'all ready for the chain rule now? Okay, chain rule. So Yeah, I'm not ready for the chain rule yet. I just want to point one more thing out to you, okay? So right now, coming into class right now, as we sit, okay? If I give you y equals sine of x, and I ask you for the derivative, everyone in here should be able to tell me the derivative of that's cosine x, right? Okay. If I say, hey, everyone, y is equal to x cubed, everyone in here should be able to take derivative of that and tell me that that's 3x squared, right? No problems? Okay, those are two separate problems. But now, what if I tell you y is equal to sine of x cubed? Now we have composition. This is sine of x cubed. We've got an inner function and an outer function. And the question is, what is the derivative, right? That's the question. And it turns out that it's not what you might think it is. I mean, I don't know what you would think that is. Maybe you would think that the derivative, that's just cosine of x cubed. I don't know. It's wrong, but I mean, you might think, oh, all I have to do is take derivative of the sine and not even care about the x cubed. Well, you have to care about the x cubed because this is not just the sine function. It's, again, it's two functions put together through composition. So somehow we have to account for the fact that there's something going on the inside other than just x itself, like x by itself. When it's x by itself, the derivative is just cosine of x. But when it's something other than just x, it's not just cosine of it, okay? So here's the rule. The almighty chain rule. It says, if you have y is some composition of two functions, f of g of x, composition, right? Then the derivative is equal to f prime of g of x times g prime of x. Okay, so I wrote it down here what this means. This first statement says, what we're going to do is we're going to take the derivative of the outer function. Whatever the outer function is, we're going to take its derivative. And then we're going to plug the inner function into it for x. So it's almost like another composition. You're going to be putting g inside of the derivative of f. That'll be the first part of the answer. Then you will multiply, and make sure you make a note here. You will multiply by, now you take the derivative of the inner function and just slap it on the outside. The word chain rule comes from the fact that this product here, this multiplication, creates a chain of two things connected together. And as you'll see as we move on, if we have triple composition, which we haven't even discussed, then you'll have, two multiplications instead of just one. But you'll see as we get there. Okay, so this first problem, I worked it all out by hand, okay? And I know it's a big freaking mess here, but let's just try and walk through it and see if it makes sense. So this is the problem we had earlier, right? Y is equal to sine of x cubed. Find y prime. So the first thing we have to realize is, from example 1 earlier, is that this is a composition of two functions. The outer function, f, is the sine function, and the inner function, x cubed, right, is going to be what we call our g. So we've identified the outer and the inner, right? So this is the outer one, and this is the inner one. Now, according to the formula for the chain rule, we need to take the derivative of the outer function, f, and plug g into it. Let's work on that first. I call that 1. Let's do this first. So first of all, what's the derivative of f? We need to know the derivative of f. So we look at f, its derivative is just
Cosine.
Of x. So the derivative of f would just be cosine of x. But what are we plugging into it? We're not plugging in x, we're plugging in g, right, into that derivative. And so we have to go back, what was g? Well, g was x cubed. So we're going to take x cubed and plug it into that derivative, which means we're going to plug in x cubed into this x for cosine, which gives us cosine of x cubed. That's just the first part. That's the hard part, okay? That's the hard part. That's the part that most people struggle with. Because the next part, times, this is just the derivative of g. That's it. So g, you take its derivative, It's 3x squared, so you just get 3x squared. And now we put them together. So what we got from the first part was this, what we got from the second part was this, and we just multiply the two together and we get this result right here. So it's cosine of x cubed times 3x squared. And what I decided to do was move the 3x squared out in front of the cosine of x cubed. You could leave it like this, but just so you don't accidentally put the 3x squared together with this x cubed, I pushed it out front. That's the chain rule. So we've got to do more examples, obviously, to get good at this, all right? Like I said, in Cal 1, I think the chain rule is the hardest, well, it's the hardest rule for sure. It's not the hardest thing we do in here, but it's the hardest rule that we have to learn. And it never goes away. Cal 1, Cal 2, Cal 3, chain rule, differential equations, it never goes away. The chain rule, if you don't know it, then it's the end of the road for you if you can't learn it, all right?
Great question though. So then after everything with the chain rule, that at the end, that 3x squared times cosine of x cubed, that's our derivative?
That's your derivative. Yep.
Okay.
So let's take a step back for a second. Let's go to the graphing software. Let's graph y equals sine of x cubed. Ooh, that's cool looking. Okay. There's sine of x cubed. All right. Now, if I wanted to know what the slope of the tangent line was right here at 1, right? Let me see. What is that value? 1.841. Right there. If I wanted to know what the slope of the tangent line was right there, then what I would need to do is what? If I want to know the
Plug
slope
in
of it, not the equation, just the slope.
You'd plug 1 into our derivative.
You'd plug 1 into the derivative, right? And whatever that answer is the answer. Okay, so what was our derivative? Our derivative was 3x squared times
Cosine of x cubed.
Cosine of x, right? Yeah, cosine of x cubed. That should be it right there. That's something ain't right. Hold on. Type that in, right? So the green one, so if I go to 1 on the green function, let me go to 1, see if it'll let me. Real close, come on. Oh, 1.621. Okay, so if I plug 1 into the derivative, I get this value. Can you all see what the y value is there? 1.621, right?
Yes, sir.
What that's telling me is, again, the y value on the derivative is 1.621. And that tells me that the slope of this tangent line, right, is 1.621. So it's the height of the point on the derivative is equivalent to the slope of the tangent line on the original function. And if you look here, let me hide this from everyone. What should the slope of the tangent line of this be at 0? What does it look like the slope of the tangent line here is at 0?
Would it be
0.
like,
It looks 0, right? Because it looks like the slope of the tangent line should be, it should be like a tangent line should go through there like that and be flat, right? Which means the value of the derivative should be what at 0?
0.
0. So when I graph it, I better see an x-intercept. When I graph the derivative, I better see an x-intercept at 0, which I do, right? I see an x-intercept right here. Okay. So this very complicated looking function actually gives you the slope of the tangent line of the original function at any point. Okay. Now let's move on. Let's move on. Okay. We can get lost in that. Okay, let's do our next example. All right, so I've changed it up for us here a little bit. What I want us to do now, why don't I give you a minute to see if you can do this? All right. So try and figure out what's the inner function, what's the outer function, and then see if you can apply the chain rule. I'll grab the chain rule here for you. I'll copy it and bring it over here so you can see it. I'll just paste it down here. Make it a little smaller. Okay, take a minute to see if you can do this. Break down the function, break down the given curve into two functions, and then try and apply the formula. I'll give you a minute and a half. Then we'll call on somebody. Cody, this is not the same problem because your outer and inner functions are different. They've traded places. The previous problem, the cubed was on the x. Here, the cubed is on the sine.
I thought you just said we could rewrite it as sine of x cubed, like one of the notes. Maybe not.
Yes, I did say that, but it would be sine of x in parentheses cubed as
Oh,
opposed
okay.
to sine of the x being cubed.
All right, thank you.
Let's go another 30 seconds. Then I'm going to call on someone. Okay, I'll take a volunteer, but don't give me an answer. I just a volunteer to help walk through this. Any volunteers?
I'll go. I'll get it out of the way.
Jorge? Yes?
Sure. Yeah.
Okay, so Jorge, I'm going to ask you some questions. So Jorge, did you identify an outer and inner function?
Yes. So
Okay.
I believe. Okay. Or
Yeah, so what did you do for the outer one?
x cubed.
X cubed? Okay, so you're looking at this as
Or sorry, or what I mean is like f of x is x
yes,
cubed.
You
Okay.
rewrote this like sine of x, but all of it cubed. And you realized that the outer function was the cubed happening. So you said, let's let the f of x, hold on. So you said, let's let the f of x be equal to something cubed, right? X cubed.
Yes.
Okay, good. And then what about the inner function? And you called it g?
Yeah.
Mm.
And then that would be sine of x.
Sine of
Or
x.
sine x. Sorry.
Okay. All right, good. Let's keep going. So if you're going to do the chain rule, you have to take the derivative of the outer function and plug g into it, right?
Yes.
So let's start with just the derivative of the outer function. What's the derivative of the outer function?
3x cubed.
3x squared.
I mean,
Right.
yeah, square. Sorry.
Okay. And now, Jorge, let's take that derivative and let's figure out what would happen if we plug the g function into it, right? Because that's that's the part that we're most interested in, right? This is this part right here, right?
Yes.
Okay, so what do you get for that?
3 times sine x squared.
Sine x, all of it squared, right?
Yes.
Good. Anyone have any questions on that? Could we rewrite it like this? Yes, right? Could we rewrite it like this? No. Okay, this is wrong. Okay, because that implies that the squared's on the x. So it's either got to be the whole thing in parentheses squared, or it's got to be the squared in front of the x. Those are your only two options, all right? This would be incorrect. Okay, Jorge, we're almost done. Now all we need is this last part, Jorge, right?
Mhm.
That last part, which is the easier part, that's just the derivative of g, which is what?
Cosine x.
Cosine x. And now we're ready to put it all together, right?
Yes.
Okay, so Jorge, y prime, our derivative is, go ahead.
3 sine squared x times cosine x.
Times, right? It'll always be times and then cosine x. And we are done. Anybody have any questions on that? Good job, Jorge. You're off the hook.
Oh,
Are ready for another one? Okay. I think I'm gonna let you try this first. I'm gonna see if y'all can figure this out. This one's a little harder, but I think it's, you know, I can sit here and show it to you all day long. You find F, find G, and see if you can apply the formula. Let me bring that formula down here for you. All right, take a couple of minutes. You know what? I think what I'm going to do is just give you a minute or two just to see if you can identify the inner and the outer. Okay. And then we'll go from there. So I'll give you a minute. Okay, I think that's enough time. Can I get a different volunteer?
I can go.
Okay, I heard Alejandro first. Christian, I'll get you on the next one. Alejandro, go ahead. What do you see as your outer function?
For the outer function, I got square root of x.
Square root of x. What do y'all think? Do y'all see that? Alejandro is saying, okay, look, I've got all this crap in here, right? But it's at the end of the day, I'm getting a square root, right? Like that's the last thing that happens. So do y'all hear what I just said? There's something subtle in the language I just used. If I were to ask you right now to plug a number in for x, right? You plug a number in, let's say I said plug in 2. You plug in 2, you plug in 2, you figure out what that is, and then at the very end, you would take the square root, right? The square root is the last thing you do, which means it's the outer function. Okay, now go ahead, Alejandro. Give me the g. What's the inside function?
That's just going to be x plus 1 over x minus 3.
The whole thing, right?
Mhm.
The whole thing. Now, Alejandro, I want you to be thinking, I want everyone to be thinking this. In the chain rule formula, you're going to need to be able to take the derivative of both f and g, right? You'll have to be able to take the derivative of f and then plug g into it. And then the easier part, you'll have to be able to take the derivative of g. Now, Alejandro, when you look at g, are you intimidated by that, or do you feel comfortable taking the derivative of that?
Maybe a little intimidated.
Okay, what do you see there? What does g look like to you? Think about last class.
Like a quotient.
Like a quotient. So yes, we can take the derivative of g, but it's going to require a quotient rule to do it. Big deal. We know how to do quotient rule now, right? So do you see, I mean, this example, I think you can kind of see for the first time this illustration of how chain rule starts to become a little complicated, because even though in the big picture you're doing chain rule, within that chain rule, you might be doing other rules within that, okay? But hey, let's just grind it out. Okay, you want to keep going?
Yeah, I got it.
Yeah, okay, so Alejandro, let's go with the derivative of f. We need that first. So what is the derivative of the square root of x?
That's gonna be 1/2 x to the negative half exponent.
Yes, that is correct. Now, do you all remember in class I told you all to try and get this hardwired where you just remember it as being 1/2 root x? Just to kind of hardwire that in. You're not incorrect, Alejandro. I'm just going to simplify your answer and get it to this, okay? I'm skipping all the steps. I'm just going to put it here. Okay, Alejandro, we are supposed to take that answer, but instead of plugging x into it, we've got to plug g into it, right? Okay, what's that going to look like? That's going to be weird, isn't it? Be 1/2 root, but Alejandro, what goes under that root?
The x plus 1 over x minus 3.
Yeah, the whole thing, right? X plus 1 over x minus 3. That goes under the root. That is the derivative with g plugged into it, right? That's what it is. It ain't pretty, but that's what it is. Okay, we are halfway there because we now have this blue piece. We now have it, right? This is the blue piece. Now we need the green piece. So Alejandro, to get the green piece, what are we doing to get this piece?
Well, it looks like you're gonna have to use that quotient rule where it's f over g and then the derivative of f times the g minus derivative g.
Yeah, all that game, right?
Yeah,
Okay, so everyone here has to realize, again, that this is like its own little problem here. Like this is like a little f up here, and this is a g. We have a quotient, and we have to follow the quotient rule. The quotient rule, if you've forgotten, then you're fired. No, if you've forgotten, don't forget anymore. F prime g minus g prime f all over g squared. Alejandro said that, right? You didn't look at a formula?
What was that?
You didn't look at a formula for that? You got that kind of hardwired already?
all right, I already got memorized.
Good. Okay, everyone should get to that point where you've got it memorized, because we're just going to be using it all the time. All right. All right. You want to keep going, Alejandro? Do you want to tell me what f prime g minus g prime, like each piece? You want to just work through them?
Sure.
Okay. All right. So give me first f prime.
Let's see. That's gonna be 1 plus 0.
Okay. So I'll just put 1. That's a derivative of the top, right, everyone? Derivative of x plus 1 is just 1. Because derivative of x is 1, derivative of 1 is 0. Add them together, you get 1. Okay, what am I multiplying that times, Alejandro?
You're gonna multiply it by the g, which is gonna be x minus 3.
Okay, good. Now I'm subtracting. So I'm right here in the formula. G prime,
And that's gonna be 1 as well,
good, times now f.
which is gonna be x plus 1.
Okay, almost there. All over.
All over g squared, which is just x minus 3 squared.
There you go. All right, let's clean this up. It's not pretty, but we can clean it up. The 1 distributes through, and so we just get x minus 3. The negative 1 distributes through, we get minus x minus 1. And then all of this is over x minus 3 squared. The x's cancel, and I just get negative 4 over x minus 3 squared. That's not that bad looking, actually. It's pretty clean, if you ask me. Okay, we keep going, right? We're not done. I think we're ready to write the final answer down here. Y prime equals the blue part, which is all this crap right here, 1 over 2 square roots of x plus 1 over x minus 3 times, because it's chain rule, you always multiply, times the green part, which is negative 4 over x minus 3 squared. This is the raw derivative. Okay. It's basically the derivative. We haven't really messed with it. There's some simplification that we can do. Are there any questions on the f or the g, or why the derivative of f is this, and why did we plug in the green part, or what the hell's going on over here? Does anyone need help?
Just a question for our raw derivative. Are you going to prefer if it's in that 1/2 of the square root of x form, or is it going
I'm
to?
actually going to clean this one up right now because I think
Okay.
it's important for you all to see the algebra. Okay. So
Okay.
look, here's what I'm going to do. First thing I'm going to do is on this first expression, I want to rewrite it as square root of x plus 1 over square root of x minus 3. I'm allowed to do that because there is a property from college algebra that says if you have the square root of a over the square root of b, you can break it up to square root of a over square root of b. That's a property from college algebra. So I have the square root of a fraction, so I break it up into a fraction with the square roots. The second fraction, I'm just going to leave alone over here. I'm not going to touch it yet. And then I'm going to look at the fact that I've got 1 over a fraction, right? This is a fraction. So 1 over a fraction reciprocates the fraction. I'm out of room. I have to move to the next page. So what I'm going to do next is I'm going to flip it. So the square root of x minus 3 is going to go on top. And now on the bottom, I have the 2 that was there, and I still have the root x plus 1 there. And that's all being multiplied by -4 over x minus 3 squared. And do a little bit more simplification. This is x minus 3 to the half over 1 times -2, and then over x minus 3 squared. Sorry, I forgot my square root of x plus 1 down here. So all I did there was 2 goes into -4, -2 times like that. I just reduced this out. And then I rewrote x minus 3 to the 1/2 power. Do y'all see why I did that? Why didn't I just leave it as a square root?
Then you
So
can fill out the x minus 3 squared, or a portion of it, right?
Yeah, like this and this is almost like having like x to the 1/2 over x squared. And then you can subtract the exponents because they have the same base. So that's what I'm going to do here. On the side here, I need to do x minus 3 to the half over x minus 3 squared, which is x minus 3 to the 1/2 minus 2. Right, I'm just subtracting the exponents. That gives me x minus 3. Let's see, if you take a half and you take away 2, you should get -3 -3 halves. And then I'm going to rewrite that as 1 over x minus 3 to the +3 halves. So I'm going to drop it back down. And so everything in yellow there is going to turn into this thing. So I still have a -2 on top. I still have the square root of x plus 1 on the bottom, but I also now have x minus 3 to the 3 halves. And that can even go further because this over here really means the square root of x minus 3 cubed. So since I have 3 factors of this, I can peel 1 factor out and be left with x minus 3 under the root. That's what this means. So I could just go one more step, maybe -2 over, let me put the x minus 3 in front, square root of x plus 1, square root of x minus 3. That would be a decent answer, pretty cleaned up. Why would I care to do all that algebra? Because maybe I want to know if this original function, where is it on the other page? Maybe I'd like to know this original function, where the hell is it, right? Is this the one we were doing? No, I'm sorry, I went to the wrong place. Here it was. Here was our original function. Maybe I'd like to know if it ever has a flat tangent line, right? Like, does it ever flatten out somewhere? I can look at the derivative right now and I can tell you no, because this is the derivative and this could never be zero because it's a fraction. And the only time a fraction can be zero is if the top is zero. I already told you that, right? So I can tell you right now, for sure, if I graph the original function, it will never flatten out. Do you believe that? I believe it because the math shows it, but I can prove to you geometrically too. If we take the square root of x plus 1 and divide it by x minus 3 and zoom out, where is it? Why is it not graphing it? Oh, I have it turned off, that's why. There we go. So no matter where you look on this graph, okay, no matter where you look, you're never going to find a flat tangent line. Every tangent line that you ever see is going to have some little slope to it. It might be really close to flat, but it'll never be completely flat. Guaranteed. You'll see that no matter what. So I remember vividly, I always tell the story to my Calculus 1 students. As a graduate student, part of what you do is, if you want to, you can work for the university. And so I worked for my university, and I was a tutor in the math lab, but then I was also a Calculus 1 recitation instructor. So basically the way they do this, like at big universities, you take Cal 1 and twice a week you go to lecture where the professor goes up there and, they're like, 100 years old and they're like telling you all the theory and stuff. And then like one day a week, like on Fridays or something, you go to what's called recitation. And that's where some graduate student stands up in front of the group of students and says, do y'all have any questions, right? And students can ask questions about homework problems and things like that. So I remember that during a recitation, I did a problem for the class or whatever, for the group of students, and I worked out the problem, but I just left the raw derivative. I just left the derivative as it's in its raw form. And I said, okay, there's a derivative. Y'all can, you could clean it up later. And this one guy showed up in the tutoring lab the next day and was like busted through the door, interrupted everyone, and was like, came up to me and was like, you need to apologize to the class because you made a mistake and all this stuff. And I was like, okay, like chill out. And anyways, he got all mad at me and wanted me to like apologize, go in front of everyone. So I said, what's the issue? So, he had this and he said, look, this was your answer. And he said, this wasn't the exact problem, but it was similar to this idea. He said, that was the answer you gave us. And then this was the answer in the back of the book, and I was like, okay, sit down. And I said, sit down, I'll teach you some algebra, and I just basically worked through the problem and showed him algebraically they're the same answer. The point I'm making with the story is that, like I told you in the beginning of class, yes, there are challenges taking derivatives. I mean, it's definitely challenging, but there's so much algebra after the derivative that comes into play later that becomes the second element of difficulty in the class. So what I recommend is that while you're working through these problems, that you try and take a derivative, try and make sure that it matches the solution in the in online. You can look at the solutions for the odd problems. Try and match your answers to those answers, because that's just gonna get you working with the algebra, get you used to it. I don't have time to go through and simplify every single one of these. I don't have time, or else we can't cover enough material. So when I get it to the raw derivative and I tell you, hey, that can be simplified, please take it upon yourself to do that, all right? It will benefit you later. And if you have trouble with the algebra, come ask for help. I can help you during my office hours.
And for the even number problems, can we use like Wolfram Alpha to give us the actual, will it show it like that? Like you're showing
It will. You have to be careful though, because with Wolfram Alpha, you run into some issues because sometimes Wolfram Alpha is just too smart. So if I say derivative of, what was it, square root of x plus 1 over x minus 3. Let's see if this answer looks like ours. I already can tell they probably did one more thing I didn't do. Oh, wow. They didn't do as much as we did, actually. Do y'all see what they did here? That's our raw derivative, pretty much. That's our raw derivative. All they did, here's our raw derivative. All they did was reduce the 2 and the -4. That's all they did. Maybe there's a more simplified form. Let me go back here. I can do step-by-step solution if I'm willing to pay, right? I think you have to pay for that, don't you? What's the other one? There's another website. Symbolab,
I use Mathway.
Mathway. Let's do Symbolab. Symbolab is also another one. So if I say derivative of square root of x plus 1 over x minus 3, see what it does. Oh, yeah, look at that. Can y'all see that?
Yes, we can. They did
There it is, right there.
one more step
That's
before
our,
us.
that was our answer, right? I went a little more, but that's pretty clean. So look, they do a step-by-step, but this might confuse you because there's so many different ways to teach the chain rule. In fact, I mean, I know there's, I've had students that have taken me, that have to retake me, and I'll teach it different the next semester. They're like, what the hell? And I'm like, I try something different each time. It just depends on the class. If they get it, good. All right, you ready? You got to move on. Not ready for version 2 yet. Okay. I'm ready to just throw a problem at you. You ready? Okay. Y equals x cubed times sine of x cubed plus 1. Find y prime. Okay, let's take 2 minutes to see if you can figure out what the hell's going on here, okay? I'm giving you no prompting on this. I'm just going to see if you can figure out. I'll just give you one hint. There's more than just chain rule going on here. There's more than just chain rule. Chain rule's here, but it's not just chain rule. So take a minute. We'll talk about it in a moment. I'm not expecting that you already got this, but before y'all get too far down a road, let's see if, can anybody kind of point out what the issue is here? What makes this different than what I've given you already?
Yeah, the sign has got it's an actual expression inside of there instead of just a variable.
Okay. So this sign with this x cubed plus 1 inside of it, that's composition, isn't it?
Mm-hmm.
You got an inner function and an outer
Right.
function, right?
Mm-hmm.
What about the x cubed up front?
Isn't it like, I guess you could say the outer, so you're gonna have like an outer with an inner that has a separate inner and outer with it. And it
Is
was
this
so-
composition though? Is this x cubed somehow
product rule.
composed
It's a
with
product,
this?
yeah.
It's a product. Y'all see that? This is a product right here. Now I didn't put it here, but everyone needs to recognize that there is a multiplication there, right?
Okay,
I'm gonna say this function, I'm gonna read it aloud in English, okay? Y equals x cubed times sine of x cubed plus 1. When I say of, that's composition. When I say times, that's multiplication. So can everyone see now with that dot there that ultimately here we have a product, right? And how do we take derivatives of products?
it's f of, or the f prime times g.
Yeah, the rule,
plus-
right?
Yeah,
So we
plus
have
g
to call this thing f, and we have to call this whole thing over here g. And
And then
then we
we're
just
gonna-
need to apply the formula, right? The formula says that the derivative of this should just be f prime times g plus g prime times f.
Then we're gonna have to do the chain rule to find the derivative of g itself.
Exactly. So now when we go to do f, here's f, right? When we go to take its derivative here, that's not going to be a problem because the derivative of f is just 3x squared. But when we go to take g and take its derivative and put it there, we have to see that g is composition, which means we have to treat it like a chain rule, which means we're going to need to go over here to the side and we're going to do some scratch work. And we're going to try and find the derivative of that g part over here, right? G is equal to sine of x cubed plus 1. And so we're going to need to work that out because that's going to be our chain. Okay. So take a step back. In the previous problem, somewhere around here, I've lost it. My pages are out of order. Where is it? There it is. Okay. So in the problem we did before, we had composition. We had an outer function and an inner function. It just turned out that the inner function was a quotient rule when we took the derivative, right? This problem, very different. We have a product rule where one of the functions is nice, we can take its derivative, but the other function is a chain rule. It's going to require chain rule to take its derivative. But at the end of the day, it's just f prime g plus g prime f. If we can figure all the pieces out, we're in business. Okay, so let's do this. Now, let's try this. See, this is where things start getting weird because we're already using f and g to notate this function and this function, right? So if g is equal to this, I can't use that formula for chain rule because the chain rule formula has f and g in it, but I'm already using f and g. Do you see what I'm saying? So like, it's like how do we want to do this? Do we want to just pretend like we have an outer function and call it f? I mean, we can. There's nothing wrong with calling the outer function here sine x and then call the inner function here the g of x, which would be x cubed plus 1. But do you see what I'm saying? It's like we've used f and g twice and they mean completely different things. And I've used g here and g is this. So you see what I'm saying? It's like it can be problematic. It's notation though. So that's why it's more important for you to understand how the rule works as opposed to all the little letters. That it's not about the letters, it's about what's happening in the chain rule. So for the first time, I'm going to try and show you a different way to think about chain rule that will not require from you that you write anything down, okay? But it requires thinking, all right? So let's see if we can do this without freaking out. If I go, let me say it this way. If I go to a Cal 2 student right now, okay? If I go to a Cal 2 student right now and ask them to do this problem, they're not going to write anything down but the answer. Like they're not going to write down inner and outer and this and that. They're going to do it all mentally. It's going to be a mental computation, all right? So that's where we want to get to. you know, it takes time, but let's see if we can't, let's just focus our attention just on this. Y'all ready? This is the fun part. Let's see how many of you can hold on to the, trying to think of something that moves fast that you hold on to or else you fall off. What would that be?
Trolley.
A what?
Like, well, I said trolley, but I was thinking like those carts in like San Francisco, but maybe they don't really move
I
fast.
don't know,
Never
just
mind.
imagine something's moving by, you need to hold on and you better hold on tight or else you're gonna get left behind, okay? So see if you can hold on to this. So the way that I picture, it, okay, in my mind, this is the way I look at this. I look at it and I see the outer and inner function. I see the outer function sine, I see the inner functions dx cubed plus 1. And what I do is I kind of like mentally imagine that the inner function is like this big blue blob of shit in here, okay? And then I literally say to myself, what is the derivative of sine of a blue blob of shit? What is the derivative of sine of a blue blob of shit?
Cosine of
Cosine of the blue blob of shit, right?
Yeah.
But I remember that it's a chain rule. So I say to myself, I still need to multiply that by the inside. And now I kind of uncover the blue blob and I say, what's the inside's derivative?
3x squared.
3x squared.
Okay. That's the chain rule in my mind. The derivative of sine of some big blob of crap. Sorry, I'll say crap instead of shit in case I'm like making someone uncomfortable. Derivative of sine of some crap is going to be cosine of the crap, chain rule, times the derivative of the crap, which is 3x squared. Now, I still need to figure out, like rewrite this because I can't leave it with the big squiggly blue thing in there. So I just replaced that blob with what it was. And that is my derivative.
Oh,
Okay. That's where you want to get. You want to get to that point where that's the way you're operating in your mind.
sine.
Now I'm going to go back now and this, now remember, this is G prime, isn't it? This is G prime. This is that part that we were going to do over here, but I told you let's not. And now let's go like get our final answer over here. The derivative of this should be, okay, let's go with, how about Cruz? Cruz, you there?
Yes.
Okay, walk me through the product rule on this. So what do you got?
Okay, so we're gonna take the derivative of f of x first, so which is gonna be x cubed.
3x
So you're gonna
squared
3x squared,
times,
and then times the g,
which is
which is sine times x
sine
cubed,
of, sine
sine
of,
of x cubed plus 1.
okay,
And then you're gonna add that to the derivative of g,
which is,
which we found over here down there,
Yeah,
which is
that's all this, right?
cosine. Yeah,
I'm gonna put the 3x squared in front of the cosine if you don't mind, Cruz. Is that all right with you?
that's fine.
So I'm just gonna move that 3x squared out front. So there's your G prime.
Okay.
And then we're not done.
You're gonna multiply it by f, which is x cubed.
There you go. So there it is. This is F prime. This is G plus this whole thing was G prime, which we had to go to the side and do. And this right here is F. There it is. Good. Okay, I'm going to give you all another one. Can I move on? You could put this x cubed right here with that x squared, make it x to the fifth. I'd probably do that if I were simplifying that. Just move it to the front because it's multiplication. All right, here's one. Y is equal to sine of 5x. Find y prime. So Justin, you there?
Yes, sir.
You cold, Justin?
Nah, I just like having blankets.
Okay, all right. So Justin, on this one, do you see composition? Do you see product? Do you see quotient? Do you see just gibberish? What do you see? What is your mind seeing here?
I'm just seeing composition,
So what's your outer function?
sine
Sine, right? And then the inner function?
is 5x.
5x. Okay, so let's see if you can walk me through this. Let's try it the short way. If I go composition here, if that's all I have to deal with, then you're going to be looking at sine of some purple junk, right?
Mhm.
So tell me what the derivative of that would be.
Of sine,
Yeah, if sine, what's derivative of sine of some purple junk?
cosine of purple junk,
Cosine of the purple junk. Now, what is the purple junk?
5x.
Okay, now you're done with doing the sine, right? You've already done that. Now you have to go to the inner function and give me the derivative of that purple junk. What's the derivative of the purple junk?
5.
5. So you tack on a 5 to this. So your answer is just 5 cosine 5x. Your answer is not cosine of 5x. Your answer is 5 times cosine of 5x. That 5x in here has an impact on things, right?
Yep.
Good. All right. We're going to turn the screws. Here we go. Y equals sine. I'm sticking with sine because it has a nice derivative, okay? Sine to the 4th of 5x. This is the first time we've done a problem like this. Okay, so note to self, this is the first time we're seeing something like this. What is uniquely different about this compared to the other problems we've done?
Exponent.
Okay, we have the 4, yes. In terms of layers, right? Everything we've done up to this point has had an inner and an outer. This one, I saw Christian put up 3 fingers. This has 3 layers to it, doesn't it? It's like you have an inner function. Let me rewrite it a different way and maybe you'll see it. We have the 5x as the inside. And then outside of that, we have the sine function. But then outside of that, we have the 4th power, the 4th power. This is a triple composition, right? It's not just 2 things being composed, it's 3 things. But let's see if we can't start to see the way the chain rule works. Again, without trying to write down all this formula stuff, because it can get very complicated. Think about it like an onion, and what we're doing is we're working our way into the onion from the outside in. So we always start with the outside layer first, and then work to the next level, until we get to the inside. So the outermost function, Bree, what's the outermost function that you see here?
X to the 4th.
Something to the 4th, right? Something to the 4th. And you said X, that's fine, but I'm not going to call it X because it's actually not just X. It's all this crap, right? The
Yeah.
green crap to the 4th, right? Is
Yes.
what we have. So Bree, what is the derivative of a bunch of green crap to the 4th power?
4 green crap to the 3rd
Green
power.
crap to the 3rd power, right? That's the outer layer of the onion being differentiated. Everyone follow that? Now, Bree, because it's chain rule, we now need to multiply by, and now we go to the next layer.
Yeah.
Okay, so I'm going to stick with you, Bree. What is the next layer? What do you see? You've already done the 4th power stuff. What's the next layer in that you see on this?
Sine to
Sine of what?
sine of 5x.
Not 5x, sine of
Oh, crap.
crap. Okay, so
Yeah,
let's
okay.
say you see now that you have sine of some yellow stuff in here. I can't do yellow. Sine of a red box. How about that?
Okay.
So Bree is seeing that the next layer in is sine of a red box.
Yes.
Yes?
Yes.
We had green to the fourth power. She took the derivative of that. It was 4 green to the third power. Now she's taking derivative of sine of a red box. Bree, what's the derivative of sine of a red box?
Cosine of a red box.
Cosine of a red box. I'll fill in the box in the green part in a minute. Chain rule, times. Now, Bree, you've done the sine, haven't you?
Yes.
Now move to the next layer inside, which is what?
5x.
Okay, and you need the derivative of that, which would be
So 5.
5.
Okay.
And now what we need to do is fill in all the pieces. So we had 4, and then it was the green box. The green box was the sine of 5x. That was the green box. All of that to the third power times cosine of the red box, but the red box was 5x, times the derivative of the red box, which was 5. And so this would give us 20 sine cubed 5x cosine of 5x. That's it. If you had 4 layers to the onion, you would start with the outer layer and you just keep working in and in and in and in. What do y'all think? Practice, right? It's going to take practice.
I mean, it seems kind of straightforward. It's just like, really, it's just recognizing what actually is like your outermost and like not confusing things.
No. I think this would be a good time to do a breakout session, and I give you a couple of problems to work on in groups. And I'm going to give you like an easy, medium, hard. Okay. That way you can get a flavor for different types of things. Okay. So here we go. Write these down. These will just be problems you can work. Okay. So for all of these, you want to find the derivative. So the first one, y equals tangent. We haven't done that one yet. Tangent of sine x. 2 y equals x cosine x over cosine of x squared. Yeah, let's just do that.
Did I just freeze or did you pause, sir, when you were talking?
I think you froze. Oh, well, no, I paused. I was thinking. Sorry, I was thinking.
Okay, I just like, I'm having the internet problems already, so
Yeah,
I'm
yeah.
behind on my chest.
Okay, last one is going to be the cube root of x squared plus 1 over x sine 3x. Now, on all of these problems, just the raw derivative, okay? You do not need to go and try and clean it up, okay? Just get me the raw derivative and I'll be happy. Everybody have those? I'm going to make the breakout rooms. Unfortunately, Zoom doesn't allow me to easily create breakout rooms and put you back with the same people you've been with before. I wish it did. But let's see, 3 to 4 people in each room, or you want to go more than that? 3 to 4, okay? 4 to 5?
3 or 4 works, whatever.
4?
Whatever works best for grouping, I guess.
Yeah. So I'm opening the rooms. I'm going to give, let's see how far we can get in 20 minutes. For some of you, you may be able to knock it out in 5 minutes. It depends on you. So, all right, enjoy. We'll come back together. We'll talk about them, and then we'll take a break. All right, Daniela, can you see them?
Yes.
Okay.
I got them. Thank you, Professor.
You should be able to rejoin that room. Is it letting you?
No.
No. Okay, I'm gonna move you to a room, then I'm gonna move you out of that room to another room. Okay, did it ask you now?
No.
No?
No.
You don't have anything popped up on your screen asking you?
Wait, sir, we did, on number 2, my group, we did the product rule on the top. We thought it was products to actually do everything, but.
Yeah, so
Okay.
we're gonna talk about this and make sure everyone's here. So how about the first one? The first one, I hope, was straightforward. We had an inner and an outer function. So you start with the outer one, you take its derivative. Derivative of tangent is secant squared of x. But instead of plugging in x, you plug in sine x. So you got secant squared sine x. And then you go on the inside and you take derivative of the inner function. Derivative of sine is cosine. Is that all right for the first one?
Yes.
Okay, now the second one, this one may have caused some issues. So let's discuss this. When you look at this, what you should see ultimately is that you have a quotient. You have everything in yellow divided by everything in green. So you have a quotient rule that you have to apply. Now I realize that the yellow is a product rule, right? When you take the derivative of the yellow, it's going to be a product. And I realize also that the derivative of the bottom is going to be a chain because it's cosine of x squared. But ultimately you have a quotient. So all I've done, I have not worked out the problem completely. I've just written down the first step, which is to just use the quotient rule. Quotient rule says you take the derivative of the top. So I wrote the top here with the derivative prime next to it, times the bottom, minus the derivative of the bottom, which I have not taken yet, times the top, all of it over the bottom squared. So are there any questions on that part? That makes sense? Okay, now I'm going to continue. So now let me do this part in green. I need to take the derivative of that. I should maybe not use green, let me use blue. So I'm going to do the derivative of this blue part. That's going to be a product rule because I have a multiplication right between there. Right there, I have multiplication. So the derivative of a product is the derivative of the first one times the second one plus the derivative of the second one times the first one. And that's everything in blue. That's the derivative of the blue part, right? Still sitting next to that is cosine of x squared. Then my minus. And now I need to do the derivative of this next part, which I'll just put in gray here. I need to do derivative of that. And that is going to require chain. I have an outer function and an inner function. So did anybody get that? Let me see. Let me call on Brian. Is Brian around?
I'm here.
Brian, did you get to a point where you had to take derivative of cosine of x squared, or do you feel comfortable taking derivative of cosine of x squared?
Yeah, that's there it would be negative sine
Okay, so I'm going to put a parenthesis because I don't want two negatives right next to each other. Negative sine of what?
of x squared.
Okay. Then?
After that you would do, or wait, what do you mean next?
Well, the
Like-
derivative of cosine of x squared, because this is composition, right? Cosine of x squared, take derivative cosine of this, that's negative sine of it. But then next to it, you need what? The chain, right?
Oh, yeah, so you would use,
Let's look at it by itself down here. We're trying to take derivative cosine of x squared, right?
Mhm.
So you have cosine of a blue blob, right?
yeah. Okay, so
Derivative
yeah,
of
so
that-
then it would be, yeah. So then you would just do for that you would do the derivative of x squared, which would be just 2x.
2x. Okay, good. Now that is just the derivative here. That's just this. Derivative cosine of something is negative sine of that something in here. Then the chain rule says multiply by the derivative of what's inside. Derivative of what's inside is 2x. And now I'm done with the chain. Now I still have to tack onto that x cosine x. And then all of that over cosine of x squared. All
I
of
had
that,
a quick question, sir.
yes.
So when I was doing mine, I did all basically the same thing. It's just on the bottom where you have or not on the bottom, but on the final version that you did at the end of the numerator, x cosine x. I actually put the, what I got for the product there. I feel that would be wrong, wouldn't it?
Yeah, no, this is not the derivative of f. This is just
Yeah.
f itself, or that's the derivative of the top one.
Okay,
I'm sorry, that's just the top one, not its derivative. We took the derivative of that here, right?
right, it's true. Okay, that's right.
Now I'm gonna clean this up a little bit, just a little bit, just because it looks weird like this. Cosine x minus x sine x. Okay, so all I did there was got rid of the 1, and then I made this plus minus a minus, and I moved the x in front of the sine x. Here, cosine squared, or cosine of x squared. Okay, I have minus minus, which is plus. And then I have a 2x and then times another x, so that's 2x squared. I have a cosine x and I have the sine of x squared. So I'm going to put the sine of x squared first and then cosine of x. That order doesn't matter, but I just chose to put the more complicated one first. There it is. That's the raw derivative, kind of cleaned up a little bit. Questions on that? I could distribute this through, but I'm not going to. I'm just going to leave it. Okay, now the last one, this one's a little weird.
I did actually have one question on two. Would we have still gotten the same thing, or is this too far ahead if we just like reciprocated that cosine of x squared just at the beginning and then took it of like the x cosine x times secant x squared?
Oh, could you have done x cosine x times secant of x squared?
Right.
Yes, you could have. The only drawback to this is you're going to have a triple product, right?
Right.
And so what you would have to do is you would have to just choose one of them, which I would probably. So what I would probably do is look at this as like, here's my product. I'll treat this like F and this like G, and then do my product rule.
You do product rule and then like a comp for the secant x squared, right?
Yeah, and then this would be composition when I do derivative of this, and when I do derivative of the F, I'm going to need a product rule.
Right. Okay.
You could have done it this way, yes. Okay, for the last one, we have the cube root of all this crap, right? So I just rewrote that as all this crap to the 1/3 power. And so if I'm going to do the chain rule, right, I have composition because it's all of this to the 1/3. So first thing I did was I brought the 1/3 out, okay, then did all of this junk raised to the -2/3. But then I still need to multiply that by, because of the chain rule, the derivative of what's in here, which I have not done. I just wrote that I still need to take its derivative. So this is the chain rule in action, is this piece that's sitting off here to the side. Now we need to do that. So how do we take derivative of this? What's going to require?
Quotient rule.
Quotient rule. So if I were to continue, I'd write this 1/3 x squared plus 1 all over x sine of 3x, all of that to the -2/3 times. Now I'm going to do my quotient rule. Quotient rule is the derivative of the top times the bottom minus the derivative of the bottom, which I'm not doing these derivatives yet. I'm just writing down what I need to do, times the top all over the bottom squared. And then when I do these derivatives, this one's going to be easy. That's just 2x. But this one's going to require what?
It's you got a product and a composition
Got
there.
a product, right? So let's just look at just this piece, just that derivative. I would have to do a product rule. So it'd be the derivative of the first one times the second one plus the derivative of the second one times the first one. So I have to take derivative of this product, so I do the product rule. The derivative of x would be 1 times sine of 3x plus, now sine of 3x, when I take its derivative, I have a chain rule there. Because I have sine of 3x. So derivative of that would be cosine of 3x times 3. Don't forget, you have to take derivative of the 3, x, which gives you the 3, and then times the x. All of that is going to be right here. And then you multiply times this. Okay. So you can see, I think, with this, these examples, I mean, the chain rule allows us to do very complicated derivatives, but it gets complicated, right? It does, you have to keep track of a lot of things. All right, it's 2:48. We're supposed to take a 10-minute break. I think this would be a good time before we shift gears and start getting into the next idea. And I mentioned this to you in the beginning of class, 8 weeks, Cal 1, right? 8 weeks, Cal 1. There will be days where we do something, and then later on that day, we're going to be needing to actually have been like good at that before we can do the next thing. And today is one of those days, because the next section requires that you understand chain rule. So I realize that not all of you, you haven't had an opportunity to go practice yet. So as we move through the next section, I just want you to keep in mind that I'm fully aware of the fact that you haven't had the opportunity to practice. And so for the homework for this section, for chain rule, you want to do as much as you can in here, right? The more you do, the better. You can never do too many problems when it comes to chain rule. Because I could show you 100 problems and then give you the 101st problem that's different than anything you've done. So it's really about being able to wrap your mind around this, just arbitrary function. It could be anything. Composition with products and quotients or mixtures, and yeah. So, all right, 10 minutes. Let's do it. We'll come back at about, let's just say 3 o'clock. Okay, meet you at 3. Let's get back to work.
Welcome back.
Yeah, you too. All right, so now
Cheers.
that you've all had 10 minutes to master the chain rule, we can proceed. So I want to show us something that I've shown you before, but we're going to need this for what we're about to do. So it's just a reminder about some notation. So when we started to introduce the derivative, the first time we ever did it, we said the derivative of some function f is the limit h goes to 0, f of x plus h minus f of x all over h. And there's a couple things I want to point out here to you. First of all, x here was what we call the independent variable. Meaning our function, the value of it depends on x. For example, if I write f of x equals, let's just take sine of x cubed. We started class with that today. This function depends on x, right? So if you plug x in, you're going to get a value out. And sometimes we replace the f of x with y. That's back from college algebra. And so we would say that y is a function of x. Okay? Y depends on x. It's independent. We call it independent because x is just whatever x is. Y is the thing that depends on the x. So y would be considered the dependent variable and x would be the independent variable. So x was our independent variable. So f is a function of x. It depends on x. Or you could say y is a function of x because it depends on x. Okay, same thing. Now, after we kind of established what the derivative was, I told you there are different notations for the derivative, right? I said you could say, all right, f prime of x. Another way you could write that would be to just write like f prime, or you could write y prime, or you could write dy dx. And we haven't used that notation much. This was the Leibniz notation. And when I told you about the Leibniz notation, I told you that there were certain advantages and disadvantages to the notations. Leibniz notation has something in particular that becomes very relevant now. And that is this expression dy over dx. What it shows you in the problem is the dependent variable and the independent variable. You can see by this expression that whatever's in the numerator here next to the d, we're saying, hey, look, this y right here, whatever this letter is, that's the thing that depends on this variable. And so that whatever's in the denominator here is what is always going to be the dependent variable. When you just write y prime and f prime, you can't tell what the independent variable, what the independent variable is. We can assume it's x. But the Leibniz notation leaves there's no gray area. The x is independent, the y is dependent. Okay? So when we were doing a problem like this, specific example, if I told you that f of x equals the function just x, that very simple function x, and I ask you to take the derivative of it, right? So find the derivative of this. Another way I could have written that is find dy dx. And that for us would just be what?
1.
1. Now I want to illustrate why it's 1. I mean, we already know that it's 1 from, I showed you the graph of the x function. It's diagonal, has a slope of 1 all the time. So I shouldn't have to convince you that the answer is 1. But what I want to show you is the notation notation makes sense that the answer is 1. So let me write something down here. If this f of x, if we call this f of x, well, let me put the y on the other side. We like to replace f of x with y, right? So another way I could have written this is y equals x, right? That's the same exact thing. Now, when we're asked to find dy dx, right? If you said, hey, find this, then what you would do is you would replace the y with whatever y is. And in this particular problem, y is x, isn't it? And so this would just become dx over dx, and dx over dx, it makes sense that that would be 1, right? Anything over itself should be 1. So this becoming this is why the derivative of x is 1. So let me present a different problem to you. I'm going to point something out that you probably, well, I know you probably never thought about this way. Let me give you an example where y is equal to, let's say, x to the 5th power. If I ask you to find dy dx, okay, those are the instructions, then what would you tell me the answer is?
dx to the 4th.
5x to the 4th, right? That's everyone, power rule, power comes down. I do not disagree. The answer here is 5x to the 4th. All right. But something that is subtle but super important right now is this. Remember, Bree, when we were doing the blue junk crap? Remember all that, right? I think we did that with Bree. If I were to look at this problem as a composition chain rule problem, then what we're doing is we're trying to take the derivative of a bunch of crap raised to the 5th power, aren't we? A bunch of crap to the 5th power. Okay, so what should the derivative of a bunch of crap to the 5th power be? Well, it should be 5 times all that crap, right? To what power?
4th.
4th power. But then chain rule says, this is the important part, chain rule says now multiply that by what? The derivative of
the
red junk, right? But what is the red junk? X, right? X. So out here, I'm actually taking the derivative of x with respect to x, and that's just a 1. And the red part gets replaced with x to the 4th times 1. And so your answer is 5x to the 4th, which is what we knew it was from the beginning. What I'm trying to point out to you is this. When you think about the derivative of x to the 5th now, I want you to be thinking 5 comes out, x to the 4th, right? 5 comes out, x to the 4th. But then chain rule says now take the derivative of the x itself. The derivative of x should be 1, shouldn't it? Should be 1. So always keep in mind that there is a little bit of a chain rule going on here. There's always this little 1 sticking out here to the side. Okay? I know that may seem like, okay, big deal. What, why are we doing that? So now I'm going to ask you a new problem or a new question. You ready? Here it is. So we have y equals x to the 5th. I want you to find dy dt. Dy dt, not dy dx, dy dt. So according to Leibniz notation, what I'm asking you is this. Tell me the rate that y changes. Okay, give me the rate that y changes with respect to the independent variable t. That should right away like confuse you because there is no t here, right? There is no t. And therefore, the answer to this is we don't know yet, okay? We can't do that problem yet. What it definitely is not, though, is 5x to the 4th. Okay, it is not that. It would only be 5x to the fourth if this was an x down here. If it's some other letter, then we still have an open question on how we do that, okay? All right, so with all that said, let's venture into the next section, all right? Leibniz notation, derivative of x is 1. If it's with respect to x, if it's not with respect to x, then we don't know.
Wait, what about the answer for number 3?
For which one?
For number 3, did we not get that one?
On the problems I asked you all to do? This you mean?
Oh, never mind. Sorry.
Yeah, I didn't finish it. This yellow part goes here, and then you have to take derivative of that still, but I didn't finish it, but I think it's, is that what you were referring to, Nathan, or no?
Yeah.
Okay. Just replace all of that right here, and then right here, replace that with 2x, and you're done.
Question.
Uh-huh.
If that y was equal to t to the fifth, then that dy over dt could work the same way as like the dx over dx?
Okay, yeah, okay, so that's a good question. So if this had been y equals t to the fifth, then yes, dy dt would be equal to 5t to the fourth, because what you're doing is you're taking derivative of something to the fifth power, so the 5 comes out, t to the fourth, then you take the derivative of t. Now, Cody, what is the derivative of t with respect to t?
1.
So yeah, it's 1. So this winds up being this 5t to the fourth.
Okay.
We'll get into this some more. Okay, don't worry. We're going to have, this is like the main idea of this. Okay. All right. So here we go. We are starting 2.6 called implicit differentiation. So far, that's spelling problem there. So far, we've been studying the derivative of a function of the form y equals f of x. That is, we have been looking at equations where we have the ability to isolate y on one side of the equation, and the other side of the equation contains x. These are referred to explicit equations. That's what they're called. And all it means is that we can express one variable, which is usually the y variable, explicitly in terms of the other variable, which is usually x. And all of the functions that we pretty much have seen in our life that we can solve for y are called explicit functions. However, some equations are very difficult to write in explicit form. Some are impossible to write in explicit form. So I'm going to first give you some examples. The ones that you cannot write in explicit form are called implicit equations. All right, so we have explicit versus implicit. So here are some examples. These are examples of explicit equations. Y equals 3x plus 1. That's a line, okay? The reason it's explicit is because I can solve for y, and y would depend completely on x. Y equals square root of sine x. Again, explicit. I can solve for y. Y depends completely on x. This last one is also explicit because I can solve for x, and the other side of the equation contains only y's. So if you give me a y, I can produce the x. But these are not. So this first equation, x squared plus y squared equals 16, is not explicit because you cannot solve for y or x easily. I mean, you can do it, but it's problematic. Let's take this and take a look at it. Does anyone recognize what that equation is? X squared plus y squared is 16.
A circle.
It's a circle of radius 4. This is a circle of radius 4. Okay, but let's see why we cannot solve that for y. Let's try solving that for y. If we try and solve for y, we could move the x squared over. We'll subtract x squared on both sides. And then to get y by itself, we must take the square root. And when we bring the square root in, we have to do plus or minus. And so what you get is y equals plus or minus the square root of 16 minus x squared. And that's actually two functions. That's not one function, that's two. Right? You have basically one of them is with the positive square root. And the other one is with the negative. Oh. And remember, the fundamental rule of a function is that when you plug something in, it can't spit two things out. And that's exactly what this would do. If I plug in a value of x, it's going to spit two things out. So this fails to be a function. And so there is no way to take that circle and write it as an explicit equation or an explicit function. Now, can we graph a circle? Absolutely, right? Let me bring my graph thing here. If I go to Desmos and I ask it to graph x squared plus y squared equals 16, it's going to draw me a circle of radius 4. There it is. Okay. So there is a graph, but it's not a function because it fails the vertical line test. Everyone see that? We fail the vertical line test here. So it's not, you can never solve it for y. This next one, x cubed. Let's look at that one here. X cubed plus cosine y equals x plus y squared. Try and solve that for x or y, and you're never going to be able to, all right? We won't even try it because you can't do it. It's not, there's no way to do it algebraically. Same with this one, there's no way. You can't get x or y by itself. I mean, you can, but the problem is, like, someone may tell me, oh, yes, you can just subtract y squared here. And now the right side of the equation is x. So, okay, you've got x by itself. What's wrong with it, though? What's wrong with that?
Still got x on the other side.
You got x on the other side too, right? So in order for me to know what x is, I would have to know what x and y are. But how can I possibly know x if I need x to get x, right? You can't do it, all right? So maybe maybe you say, oh, bring the x cubed over, right? So subtract it on both sides. So maybe you say, okay, there you go. Well, this still isn't solved for x, because if you give me a y, that doesn't tell me what x is. That tells me what x minus x cubed is. And that's not what we want. We want to know what x is. So again, you can't do it. Now, is there a graph that goes with that? What do you think?
Yes.
Yeah, that's got to be, hold on, x cubed cosine y, x cubed plus cosine y,
Equal to x plus y squared.
x plus y squared. There it is. Oh, that's cool. Look at that. It's not a function, fails the vertical line test, right? But there is definitely a curve that goes with that equation. And let's look at the last one. Cosine of x times y
Equal to 1 minus sine of y.
Oh. Wow. Okay, that is a pretty crazy looking function. Wouldn't you say? Well, sorry, it's not a function. I should have never called it a function. That's a pretty crazy looking curve or relationship between x's and y's, right? So remember, to actually be the green graph that we see here, right? The green graph says, look, if we pick a point, right? Like if you pick some point here, it has an x and a y value. And if you plug those values into this equation, it should be true, okay? That's all it says, but it's not easy for us to do because you can't solve this for x or y easily, but the computer can graph it, which is nice. Okay. Where do you think I'm headed with all of this? What could we ask about any one of these graphs? Let's start with the circle. What can I ask? Think calculus here.
The tangent is, like what the
What the
tangent
slope
is at a certain
of the
point.
tangent is at a certain point, couldn't I? So like if you pick me an x value, okay, go here, let's pick an x value. Let's just say 2, okay? What's the slope of the tangent line at 2? Well, what's wrong with that? At 2, there's 2 different points, aren't there? At an x value of 2, there's 2 different points. So if you're talking about the point on top, I'm gonna have a slope of a tangent line up there, that's a certain slope, but if I talk about the one at the bottom, that's gonna have a different slope. So do you see that just telling me at x equals 2 does not narrow it down enough for me? I would actually need to know whether or not you're talking about the point on top or the bottom, right? So you would need to give me more than just x. You would actually need to give me the y value also. So you'd also need to give me whatever y value you're talking about here. If we do this for the other curve, this one, we run into the same issue. If you go and pick some value of x, let me zoom in on this. If you go and pick some value of x, let's say I pick right here, whatever that x is. If I go up, I've got this point. If I go down, I got this point. Well, you know what? Those look like they'd have about the same tangent. So let me pick here, x. If I go up 1 point here, 1 point here, one of them has a slope there, the other one has a different slope, right? So again, it doesn't look like I'm going to be able to get the slope of the tangent line unless you give me more information than just the x. But they exist, don't they? I mean, tangent lines do exist on this curve. It's just a matter of can we get them, right? So this one, oh shit, look at this. I mean, this one's crazy because if you pick an x value, okay, so if I pick some arbitrary x value, let me zoom out. No, I'll just go here. So if I say I pick x is 3, then we have 1 point, 2 points, 3 points, 4 points, 5 points, 6 points, at least 6 points that all have different slopes of tangent lines. At each of those 6 points, there's different slopes. So how are we going to figure out what they are, right? Well, there's a way, okay? There's a way to do it, but it requires a new type of taking derivatives, a new technique. It's this is not a rule. You know how we learned power rule, product rule, quotient rule, chain rule? We learned those rules. This is not a rule. This is a new technique for finding derivatives when you have implicit equations. When you have implicit equations, how do we find slopes of tangent lines? Okay. So how do you do it, right? So here's how we do it. We're going to start with the very first one. X squared plus y squared is 16. If x squared plus y squared is 16, find dy dx. In other words, what I'm asking you to find is y prime, right? Now, again, understand the difference in those two notations. The dy dx is telling me that x is the independent variable and y depends on x. This notation doesn't tell me that, so we just have to understand that that's what we mean, okay? The derivative of y, we are kind of like assuming, and this is why this notation sucks, we're assuming that x is the independent variable. This, there's no gray area. We know it is, okay? So here's how we're going to do it. You ready? Here's how we're going to do it. This is called implicit differentiation. Okay, so here's what you do. You write down the implicit equation. And then what you're going to do is you're going to do something to both sides of the equation. And what you're going to do is you're going to take the derivative on both sides of the equation. So I'm going to take the derivative with respect to x, meaning that I'm going to treat x as the independent variable. I'm going to do that derivative on the left side of the equation. And I'm going to do the same thing. I'm going to take the derivative with respect to x of the right side of the equation. Now, just so you understand this notation, the dx on the bottom again is telling me what the independent variable is. The d with nothing next to it just means, hey, we're going to take derivative of that, the derivative of that. We're going to take derivative of this thing, treating x as an independent variable. We're going to take derivative of this thing, treating x like an independent variable. like the independent variable. All right, now, on the left side, we have plus, right? And anytime we take the derivative and we have plus, we can do them individually, can't we? We learned that about derivatives. If you have pluses, you do them individually. So the left side of this becomes the derivative with respect to x. We're gonna take derivative of x squared first, plus then we're gonna take derivative with respect to x of the y squared. Okay, then that will be equal to the derivative with respect to x of the 16. There's nothing really to do on the right-hand side. All I'm doing here is using the property of differentiation that if you have addition or subtraction, you can do them individually. Now, here we go. This is where things start getting a little wobbly for people. Remember when I started this? I told you that from now on, I want you to be thinking about taking derivatives as, you know, like x to the 5th, which was like a day ago, 2 hours ago, x to the 5th, everyone's taking derivative of that, just saying 5x to the 4th, and you're done. You need to be thinking a little harder now. The derivative of x to the 5th, you're looking at as something to the 5th power. The 5 comes out, x to the 4th, then you have to take the derivative of this base. And when you take derivative of that base, you need to pay attention to what the independent variable is. Let me illustrate. Okay, we're ready to take derivative of x squared. Okay, so x squared is something squared. What's derivative of something squared? 2 times that something to the first power, right? That's what the derivative of that is. But now chain rule says times the derivative of the base. What's the base of this thing?
X.
X. I need to take the derivative of that x with respect to what? Well, what's my variable here?
Dx.
X, right? So with respect to x. Now, what is that going to turn into?
A 1.
A 1. Okay, so, but I'm not going to write it. I'm just going to leave it, okay? Then we have plus. Now, the next one, I need to take the derivative of y squared. Let's call on somebody. How about, is Roger here? I don't see Roger. Gabriella?
Yes, sir. Okay, I'm gonna take a random guess to like think ahead, I guess, but wouldn't it be like when looking at the original equation, 2x plus 2y dy dt equals 0, and then you're solving for dy dt, or is that something else?
That's exactly it, but let's go a little slower. Okay, so when you take derivative of y squared, you're saying that that's equal to what?
2y dy dt.
Slow down, 2y, because the 2 comes out, right? Y to the first power, right? Everyone got that part? Times, now this is the important part that Gabriella obviously knows and understands, is that Gabriella is looking at the base, but this time, Gabriella, the base is y, right? And you're
Yes, sir.
taking the derivative of that base, dy, with respect to what variable?
dt.
With respect to x, right?
Oh,
Sorry,
dx.
x.
Okay, my apologies.
So dy dx. Gabriella, is that 1? Is dy dx 1?
I wanna say yes.
What about dx dx? Dx
That
dx is the same thing over itself, right?
That would be 1, but in this
That'd be
case,
1.
the dy dx is not.
This is not, right? Does everyone
Right.
see that? Does anyone have any questions of where the hell this dy dx came from? 2 comes out, y to the first power. Take the derivative of the y with respect to x, and it is not 1, it's dy dx. But Gabriella, aren't we like jumping for joy right now? Well, we're not, but isn't the original problem asking us for dy dx? Isn't that what they want us to find? And haven't we somehow miraculously produced it now? It's here, it's right in front of us. There it is, right? That's the thing we're going to be looking for. Does everyone follow that so far? We're not done. Now, we are done with the derivative of y squared. That is 2y to the first power times the derivative of y with respect to x, which is dy dx. And then Gabriella said equals, because we're done here, we just move on equals. And then Gabriella, you said that the derivative of this was 0?
Because it's a constant.
Because it's a constant. And look, no matter what world you live in, okay, the derivative of a constant is always 0. Because remember, the derivative is telling you the rate at which something is changing. And if you're talking about a constant, it's never changing, no matter what. So that will always be 0. Good. Y'all good with this? That's implicit differentiation. Let me clean it up. Gabriella, you're off the hook. Thank you. This is going to be 2x.
Okay.
Now we said that this dx, that is a 1, so I'm not going to write anything, plus 2y. Also, these are 1s. Just be careful. These things in blue here, those are 1s, not primes. Don't mix it up with I'm not saying it's a derivative. I'm saying the number 1. So we have 2y there, and then next to that, we still have times dy dx equals 0. And the goal of the problem is to get dy dx, to figure out what it is. So all I'm going to do now is isolate it. This is just going to be algebra. I'm going to move 2x to the other side. So subtract 2x on both sides. And then to get dy dx by itself, I divide both sides by 2y. And I get a final result that dy dx is equal to negative 2x. Oh, sorry, I'm going to simplify that. Negative x over y. And I'm going to box it up. Negative x over y. Any questions on any of that yet? I still have more to say about this, but are there any questions on it?
Just making sure we know we're functioning off of the x in this because you had d over d of x at the beginning.
What's that?
1 second, sorry, my dog.
Okay. Okay. If you go back and you look at every problem we've done up to this point in this class, when we have taken a derivative, no matter what it's been, okay, even today, look at any of the derivatives that we've done. Our answers have always just had x's in them, right? Just x. There's never a y in any of these answers. Always x. Always x. And that's because the original curves that we're looking at are functions, right? Every one of these curves we were looking at was a function, which means if we want to know the slope of the tangent line, all we ever really needed to know was the x it came from, right? So give me the x and I'll give you the slope of the tangent line. Here, our answer doesn't have just x in it, does it? Look at our answer. The derivative is equal to negative x over y. It has both variables in it. Now, is that a good thing or a bad thing? Think about the picture. Remember when I was talking about this circle? And I said, hey, if we just knew the x, right? If we just knew that x was, let's say, 2, that wouldn't be enough because I would need to know if I'm talking about that point or that point, right? But the derivative that we got, dy dx, says, you know what? If you want to know the slope of the tangent line, you're going to need to know what negative x over y is. That means you're going to need to be able to provide me both the x and the y coordinate. As long as you provide me both the x and the y coordinate of the point you're talking about, this will spit out the slope. That makes sense? So let me do something here. Let's take a point. How about we take this point? Because I think this is probably the easiest for us to do. What if I went 45 degrees up to this point? Now, you may not be able to tell me what that point is, but would you agree with this? Whatever this number is exactly the same if we're at 45 degrees, right? These are the same numbers. Yes?
Yes.
45 degrees, you go out, you go to the right, the same amount, you go up, okay? Because you're at 45 degrees. These, whatever x is, that y, they have to be the same. So if the formula says to find the slope of the tangent line here, to find that slope, you need to use that formula, then you just have to take negative of the x coordinate, which in this case would be negative of some number, divided by the y, which is the same number in this particular case for 45 degrees. And what would that become? What's negative of a number divided by that number?
Negative of the number, or negative
A
one,
negative
yeah.
one?
-1, right? And so the slope of the tangent line there would be -1. Does it look like it's -1 to you? Does that slope look like -1?
Yep.
Yeah.
Oh, well, yeah, the slope, yeah.
No. What about, okay, so what about this? What if you took this point right here and we want to know the slope of the tangent line there? Can anybody tell me anything about that point? Remember, this circle has a radius of 4. So
Say
what's
0,
the
4.
x coordinate and y coordinate?
0, 4.
0, 4, right? The x is 0, the y is 4. Plug that into this formula and what would you get?
0 or
So-
undefined.
dy dx would be negative x over y, but that would be negative x, the x is 0, the y is 4, and that is 0, right? 0 divided by anything except 0 is going to be 0. And do you agree that that line has a slope of 0? Right there. Right? It's flat. Let me do one more. What about this point right here? There's your tangent line. That point is the point -4, 0. That's your x, that's your y. So if I wanted to find the slope, I would use that formula, dy dx equals -x over y. And let's see, x would be -4, and then what's the y?
0.
0, uh-oh. Division by 0 is undefined, right? But
It's like a
remember,
vertical.
vertical lines, the slope of a vertical line is undefined. 0 slope, right? Positive, negative, but straight up is undefined. And it matches what our formula is spitting out, right? This, I mean, I don't know. I find that pretty amazing. We took the equation of a circle and now we have a new formula that will generate the slope of the tangent line at any point on the curve. You just have to give me the point. As long as you give me the point, I can give you the slope. And you might be asking yourself, like, why, you know, who cares, right? I know that's always a question I get in these classes, who cares? But in the real world, okay, in the real world, when we're studying something like, when we're talking about derivatives, think of it as like an object. I'm going to say, let's say we're looking from the top down, and let's say I have a car that's driving around, right? Then the tangent line, that slope in physics can later represent what's called the velocity. And you can start looking at it as a vector, and then it can give you not only the direction, but the speed of the car at that time. So this has implications later. But the problem with what we've been doing so far is that everything we've studied has to be a function, so it has to pass the vertical line test. But in the real world, not everything behaves the way we want it to behave, right? Like if I were to just put, if I were to go outside and grab a little roly-poly, right, and put them on the page here, here's my little roly-poly, and just let them start walking around. Starts walking, and I'm like, okay, great, I can go to any point on your path and I can find the velocity basically using a derivative. I haven't shown you how to do that, but imagine you could. And then all of a sudden the roly-poly does this, turns and goes back like this. I'm like, shit, stop, wait, hold on. I can only do calculus if you stay past the vertical line test all the time. Well, the real world doesn't work like that. So we need to be able to find slopes of tangent lines, even if the curve is not a function. And that's what we're doing here. We're finding a way to find slopes of tangent lines for paths that are not well behaved. Hope that makes sense. Okay. Let's try this next one. Okay, so what we want to do here is we want to find What I'm telling you to do is find dy dx. It's implicit. I can't solve for x. I mean, yeah, I can't solve it for y. I can't get y by itself. So what I'm going to do is take the derivative with respect to what variable? What's the variable on the bottom here?
X.
X of the entire left-hand side. And set that equal to the derivative with respect to x of the entire right-hand side. And at this point, we try and recognize things we can and can't do. And I see pluses here and here, which allows me to break this up into two separate derivatives, one here, one here. I can do the derivative of each one because of the pluses. Any questions there? Marissa, are you here? Marissa,
Yes,
Marissa.
I'm here.
How's it going, Marissa?
I'm good. How are you?
I'm hanging in there. All right, Marissa, here we go. Let's see how, if you're understanding this. So the first task, Marissa, is for us to take the derivative of x cubed, right? With respect to x. So Marissa, we see something to the third power. What's the derivative of that?
3x squared.
Okay. Now, this is the critical part, Marissa. Do you see you still have work to do as far as there's a chain rule and you now have to take derivative of the thing that was here? You
I'm sorry,
understand
can you
that?
repeat the question? Oh, yes.
Okay, so we need to take the derivative of what with respect to what?
Of x.
Okay, the derivative of x, so derivative of x with respect to. So what's the variable on the bottom here?
X.
X, okay. And dx over dx will become a 1. Let's keep going, Marissa. I'm done with that. Move over. Now, again, be very careful here. Marissa, we are taking the derivative of cosine of something, right? It's cosine of something?
Mhm.
So the derivative of cosine of something should be what?
Negative sign.
Negative sign of that something, right? Whatever it is.
Mhm.
Okay, chain rule though, Marissa, you now need to go and take the derivative of what's inside. So this was a composition, Marissa, right? It's cosine of y. You take the outer function's derivative first, negative sine of y, and you multiply that times the derivative of the inside function. Marissa, what's the derivative of y with respect to x? How do I write that?
Dy over dx.
Dy dx. And are you happy to see that?
Yes.
Elated? Not quite. Happy? We'll go with happy. Dy
I think yes.
dx,
Yeah.
right? We're happy to see that because that's what we want to find in the, I mean, that's what we're looking for, right? So we're happy to see it. All right, let's move to the other side. I'll let you off the hook because I need to get through some more students here. Jair, you're up.
So you would have to find the derivative of x, which would be 1.
Okay, Jair, is it all right if I write it this way? You said we need to find the derivative of x with respect to x also, right? So we're taking derivative of this x with respect to x, which will turn out to be 1. I
Yes.
agree. Okay, plus now here, Jair, what do you got?
It is 2y
Okay,
and then times dy over dx.
perfect. Okay, so Jair said, all right, derivative of something squared, the 2 comes out. There you got your something to the first power. You don't need to write the 1, but I'll put it there. Then Jair said, okay, now I need to look at the base and take derivative of that base with respect to x. And that's dy dx. So look, again, it appeared again, didn't it? It's appeared twice. All right, I'm going to rewrite the problem. I'm going to replace all the dx's with 1. All the dy dx's I'm going to leave alone. There we go. So that was a 1. That was a 1. That stays, that stays. And we're trying to get this by itself. Right? We're trying to get the dy dx by itself. So here's the standard procedure once you get to this point. Any terms that have dy dx, move them to one side of the equation. Anything that does not have dy dx to the other. So that means I'm going to, this whole term has dy dx in it. That whole term has dy dx in it. So I'm going to choose, you can choose which side to move things to. I'm going to move this one to the right. And then this one, I'm going to get it out of here because it doesn't have a dy dx. So I'm going to move it to the left. So when I move the 1 to the left side becomes 3x squared minus 1. And when I move the negative sine y dy dx to the right, it becomes positive. But I still already had over there this piece. Any questions on that? That's just the algebra of moving things around.
Right, then can we just factor out the dy over dx and then divide
Yep.
it by the other side? Okay.
That's exactly why we do it. We do that so that we can factor out on the right-hand side the dy dx. And when we factor it out, we should be left with a 2y plus sine y. They both had dy dx. We pull it out. We're left with the 2y here and the sine y and the plus between them. And now finally, to get this out of here, unfortunately, I have to divide by the whole thing. It's the only way to do it. So whatever I do to the left, I do to the right. And so my final answer isn't going to be pretty, but it's going to be an answer. 3x squared minus 1 over 2y plus sine y equals dy dx. So if somebody wants me to find the slope of the tangent line, they're going to have to give me both the x and the y coordinate, or else I won't be able to do it. And that's exactly what the picture said, right? This was the problem we just did. You're going to have to give me the x and the y coordinate of the point you want me to look at, or else I'm not going to be able to generate. There we go. Why can't I? Won't let me grab a point on here. Oh well. You have to give me both the x and the y coordinate. That way I can, just distinguish between the top or the bottom. All right, we have another one to do. What time does our class end?
4:30.
Hey, don't let me go past like 4:20 because I need to talk about the test. All right, this is implicit. I want us to find dy dx. All right, so I'm going to take the derivative with respect to x. I know that because there's an x down here. That's why I'm doing it with respect to x here. You'll see why that's important later. Of the left side. And that'll be equal to the derivative with respect to x of the right side. I do see a subtraction here on the right, so I should be able to split this up into the derivative with respect to x of 1 minus the derivative with respect to x of the sine of y. On the left-hand side, I can't split anything up because I don't have any pluses or minuses. So that's just going to be the derivative with respect to x of this. All right, so here we go. Let's do the right side first. The right side's easier. So Matthew Diaz is up. What do you got? Are you here? Are you here? You're on mute. We can't hear you. Is it not working?
Oh, sorry, did you say my name, sir? I couldn't hear.
Yes, I did. Matthew Diaz, yep.
Oh, I'm sorry. What was the question again?
Help us out with the derivative of the right side. We'll leave the left for now. Let's just do the right.
Okay.
So what about the derivative with respect to x of 1?
It'll just be 0.
0, because derivative constant is always 0. Okay, so here's the part that's tricky. So the derivative with respect to x of sine of something would be what?
Would it be cosine?
Yeah, now this is going to be like a composition. It's outer and inner, right? So you do derivative of sine of something, you said would be cosine of y, right?
Mm-hmm.
But you've got to finish off the chain rule. What am I going to multiply that by now?
Times d of y over d of x.
Perfect. Does everyone see that? Derivative of sine of y is negative, no, not negative. The negative's from here. Derivative of sine of y is cosine of y dy dx. Good. You seem like you understand that. That means you probably can do the left side for us too. Yeah. So the left side's a little complicated. Everyone pay attention. This is about to get a little weird here. So Matthew, you've got cosine of something, right?
Mm-hmm.
Cosine of something. What's the derivative of cosine of something?
A negative sine of something.
Okay, so negative sine of the something, which is x times y. Okay, you're done with the cosine. Now, Matthew, you have to multiply that by the derivative of what's in here. And what do you see there?
X and y.
Being what? How are they together? What's the operation between them?
They're multiplied.
Multiplied. And how do we take derivatives when there's multiplication?
With the product rule.
With the product rule. Right? We've got to do a product rule on the inside piece. So I'm going to give myself a big parentheses here so that I can get the product rule on here. Now, Matthew, Matt?
Yes.
Do you feel comfortable with the product rule on this? Can we walk through this?
I think so.
Okay, so what is the derivative of x with respect to x?
A 1.
1. I'm going to write it down as dx, everyone. You'll see again y later. That's going to be a 1. So that's the derivative of the first one. Then the product rule says what, Matt?
You multiplied that by y.
By y, and then plus, and now, Matt, what's the derivative of y with respect to x?
Is it dy over d of x?
Dy dx. Good. And then finish off the product rule times
Times x.
X. There we go. There we go. Cleaning up. Good job, Matt.
Thank you.
There we go. Okay, so all I did was replace that with a 1. 1 times y is y. Everything else kind of had to stay, except that 0 went away. So there it is. I've got the derivative done. Now I've got to get dy dx by itself. And I have a problem. Does someone see the problem I have getting dy dx by itself? I can't just move it over right now.
Yeah, you're gonna have to deal with the negative sign xy, which is a composition as well.
Well, this is multiplication. That I need to free this dy dx up. I need to get it out of there. It's inside a parenthesis. So all I'm going to do is distribute this through. Now, look at what that's going to become when I distribute. Negative sine of x times y gives me negative y sine xy. That's the first distribution. The second distribution becomes negative x sine of xy dy dx. So when I multiplied this times this, I just chose to put the x here out in front of the sine of xy, and I left the dy dx here. That was just my choice. I could have just put, you know, negative sine xy times dy dx times x. And on the right side, cosine y times dy dx. And now we just move all of our dy dx terms to one side. So I'm going to take this and move that to the right. And that's the only thing I need to move because this already has dy dx in it. So I'll be left with negative y sine of xy equals negative cosine y times dy dx plus x sine of xy dy dx. I know this is tedious. This came over to the other side, so it became positive. Factor out dy dx on the right. I've never really enjoyed solving for dy dx. It's usually a pain in the butt. Factoring dy dx out of both of those, we're left with this. And then finally, we divide both sides by that. And that's what dy dx will be. It's equal to this side right here. Okay. Again, notice in order for me to know, in order for me to be able to tell you the slope of the tangent line on this curve, you're going to have to give me both the x and the y coordinate. And we already saw that picture was massively crazy, right? So as long as you can give me a point, I can tell you the slope of the tangent line there. It's pretty powerful stuff, the implicit differentiation. All right, deep breath. Everyone all right? Okay. It's time for me to turn the screws a little more. No problem. If y, let's say y plus x squared equals y squared plus sine x. I want you to find dx dt. Uh-oh. Okay, this is the first time we've seen this. Now, before we even do it, okay, I want you to try and understand what this is asking us for. This is asking us for the instantaneous rate of change in x relative to t. So it's basically if you change t just a little bit, how much does x change by? When we were doing this problem, we want to find dy dx. We're saying if you move x over a little bit, how much does the rise? It's like rise over run, right? It's dy is the change in y, dx is the change in x. So a little change in x has what impact on y? And that gives you the slope of the tangent line. This is saying a little change in t, how does it impact the x? But that should be like that should seem like a stupid question because there is no t here, is there? You'll see there's no t here? We can still do it though, okay? Let me show you how. What we're gonna do is we're gonna take this equation and we're gonna take the derivative with respect to what variable?
T.
T,
Yeah.
right? Because that's the one on the bottom here. We're gonna do that on the left side. And we're gonna do that on the right side. On both sides, we have addition. So that means I can even split that up more. So I'm just using the fact that there's addition to do each one of these separately, all of them with respect to t. And now we need the drum roll and we need Caitlin. Where's Caitlin? Is Caitlin here? I don't see Caitlin. Nathan, you there?
Yes.
All right, Nathan. You doing okay, Nathan?
Yeah, just finished writing
Hanging
it.
in there?
Yeah.
Okay, I'll try and help guide you through this. The first part, we need, Nathan, the derivative of what with respect to what?
Derivative of y with respect to t?
So dy dt, right?
Yes.
Okay, and that is not one, right?
Correct.
That's just dy dt. Whatever the hell that is, that's what it is, right? Okay, we're gonna keep going, Nathan. Plus, now careful here. What is the derivative of x squared with respect to t? So what's the derivative of anything squared?
It would just be 2 times that number.
Okay, 2 times that base x, right?
Yes.
So you brought the 2 down. That
And
becomes a 1 up
multiplied
there.
by dx over dt.
Perfect, dx dt. That's the chain rule. After the 2 came out, popped out, became a 1 here, then Nathan said, oh, I've got to take derivative of the x also with respect to t, which is dx dt, which is not 1. But Nathan, that is what we're looking for, isn't it?
Yes.
So we're happy to see it. You're doing good. Let's just keep going across. Equals. All right. The derivative of y squared with respect to t.
So it'd be 2y times dy dt.
Perfect. See, once you see it and catch on to it, it becomes easy. It flows, okay? And that's not 1, right, Nathan? Dy dt is just, we don't know what it is, dy dt, whatever it is. Okay. Plus, all right, last one. Let's see if you can go 100% on this. I feel good about it. The derivative of sine of x with respect to t.
Would it be cosine of x multiplied by d sine?
No,
Or is
you
it
already
just
took care of the
dx?
sign.
Yeah.
dx dt, right? Yeah, so you had it. Derivative of sine of something is cosine of it. Then you have to take derivative of what's inside, which is dx dt. And that again is what we're trying to solve for. Good job. Good job. So now what we do is we move everything that has dx dt to one side, everything that doesn't to the other. So I'm going to do that now. Dy dt is going to stay. I'm going to move this guy to the right. I'm going to move this guy to the left because this one doesn't have dx dt in it. This one does. So when this comes to the left, I get a minus 2y dy dt equals on the right, which I still have this cosine x times dx dt. And then I'm bringing this guy over, so it's minus 2x dx dt. factor dx dt out. Almost there. Cosine x is left when we factor it out here, and then minus 2x is there. Finally, we will divide. So we're trying to get this by itself, right? So we're finally now going to divide by this on both sides, and this will be my final answer. I'll write it nice. dy dt minus 2y dy dt over cosine of x minus 2x equals dx dt. All right, Christian, you're up. Give you a second. You still writing down? Are you good or what?
I'm still writing that down.
Okay.
Okay, I'm ready.
Okay, so I have a tough question for you, Christian. When we were looking at the previous problems that we've been doing, right? I've tried to point out at the end that in order for us to know the slope of the tangent line, you're going to need to know x and y. So you're going to need to know the point on the curve, right?
Yeah.
This problem, when we started it, we wanted to know what dx dt meant, which I said was, if you change t a little bit, how does x change? And I said, that should seem weird because there's no t in here at all, right? But if we ignore that for a moment, Christian, at the very end, in order for us to know what dx dt is, what would we have to know? What is this telling us we would have to know?
We would need x, y, and
We would have to know x, right? Someone would have to tell us what x is. Someone would have to tell us what y is, and what?
t, or the derivative of y in relation of t.
Exactly. Okay, so here's what I'm saying. If I want to know how x is changing with respect to t, I need to know not only what x and y are, but I also need to know the rate at which y is changing with respect to t. If you can provide me with all of that information, I will tell you the rate at which x is changing with respect to t. Now, again, it seems strange because there's no t here, is there? There's no t. But now, think about this. I'm going to type this in. No, I'm not going to type it in. It's going to take too long. I'll type it in. I have no idea what this is going to look like because I just made it up. Can somebody read it out to me? What was it? Y plus?
Yeah, you got y plus x squared is equal to y squared plus sine x, is your original.
Oh, that's cool. It's like a crazy X, right? It's just kind of a free going X, right? It's just kind of wobbly. That's the graph of that curve, okay? So what I want you to think about now is that obviously there are, well, I hope it's obvious to you, that if I pick some point on this curve, it has an X and a Y coordinate, right? There's no T here. But imagine that T now is time. Okay, so it's like you have a particle moving along the curve, and it, like, let's say that this is T1, and then it moves to here at T2, and then maybe it's here at T3, you know, so it's moving. So as it moves along this curve, we want to know what we were asking for is, what were we asking for? Dx dt? That's asking at a specific point. It's saying at a specific point, if you pick a point, can you tell me how much the x coordinate is changing? X is left and right. Can you tell me how fast the x coordinate is changing as time changes? It's like an instantaneous rate of change in the x coordinate at any point in time. And the answer, like Christian said, says that in order to answer that question, you've got to know where you are, x and y, and you need to tell me how fast the y is changing. Then we can answer the question. So all of a sudden, this third variable t can be looked at as like a clock running in the background, which is very applicable to the real world, right? Things happen, things are in motion, time's always this thing going in the back. Okay. What do I want to say? No more, I don't think I want to say anything more about that at this time.
You had mentioned you wanted to say something about the test. It's 10 minutes early, but I just thought I'd remind you. So
Yeah, I think I'm ready to start talking about that. I want to share a story with you. I share this story with my calculus classes. At this point, we can just kind of take it, just exhale. We're done for the day. We still need to do more with implicit. Okay, there's more to do, but we'll do that after the test next week. For homework for this, I would say for the implicit, let me just look at it real quick. Just tell you what to focus on for now, because I don't want you to try and do things you can't do yet. I would say for implicit, only do up through the first 13. That'll keep your mind somewhat sane, because you still have to do all the chain rule stuff. Okay, that's going to be a monster right there of homework. Okay, so just stop here and we will get to these Tuesday after class. You'll be able to do these.
just have that stuff done by next Tuesday, preferably.
I would say by next Tuesday. I mean, you're probably just going to be focusing the next day or so on the test. So after that, after Thursday, well, actually Thursday, I'm going to finish this. I apologize, because our test is only going to be half the class period. So we'll talk about the test in a minute. Okay. But all right. So let me share this story with you. It ties into what we're talking about here today. It's a true story. I feel like I've told you all this story. Told you about the going out to the club when I was.
Yeah, the woman you asked her about what's the derivative of X, and then you asked her one other question, I believe, and then she knew both, shocked you.
Yeah. So
You're friends with her
if
still?
you remember that story, I don't have to tell it again. Good. When I asked her what the derivative of X was, her response to me was with respect to what variable? Okay. Now think about that. Before today, if I asked you what derivative of X was, you're going to be saying 1, right? But what we've learned today is that it matters what variable you're treating as the independent variable. So if I want to take the derivative with respect to X of X, then of course, yes, that's dx over dx, and that's going to be equal to 1. But if I say, this is basically what I asked her. I said, what's the derivative of X? But when you say it like that, you're not being specific about what the independent variable is with respect to what. So her response to me was like more than I ever expected. She was basically asking me with respect to what? If it was with respect to X, her answer would be 1. If it was respect to T, her answer would be dx dt. What that demonstrates is an understanding of derivatives beyond what I guess I would expect from normal people, right? I mean, most people just say 1. So pretty cool. All right, well, the test. All right, so a couple of things about the test. Let's bring up the review. Give me just a minute. I'm going to step away for just a moment. I'll be right back. Give me 2 minutes. Okay, you know what? I'm gonna show you the solutions instead, because I already sent those out. A couple of things I wanted to point out on the solutions to this review. Zoom out. So this first exam review, like I said, was given last spring. I just copied it and gave it to you. When they took this exam, they did not have the shortcut rules yet. So when it came to problems for derivatives towards the end, that's problems 13 and 14, asked to find the equation of the tangent line. They only had the limit. They didn't have product rule, quotient rule, chain rule. So for you, I am going on the test, I am going to tell you on just a few problems, maybe one or two, I'm going to tell you to find the equation of tangent line, and I'm going to tell you using the limit definition, which means you will have to find that derivative using the good old fashioned limit h goes to 0, f of x plus h, all that stuff that we did in class. You'll have to do that, okay? For at least one or two problems, you'll have to use the limit definition. That's different than the review. The review didn't state that because, like I said, they had no idea what the product and quotient rule and chain rule was when they took the test. So they had to do it that way. That was the only way they had. So that's what I will expect that you do, all right? Now you can use the product rule, quotient rule, chain rule. You can use it to check your answer, okay? But on paper, if I say use the limit definition, that means that I need to see it with the limit. Cody?
So that just means like you want either the limit of h approaches 0 of the f of x plus h minus f of x over h, or the f of x minus f of a over x minus a, right?
Your choice.
My choice.
Yep, your choice.
But you want that scratch somewhere that you can see instead of just the rules. Right.
Yeah.
Okay.
Because like for a problem like this, it would show that you know how to come in and like do conjugates and things like that. And, you know, there's the algebra in that. Okay. Now, let me see. 223. Let me see something here. Let me see if I can. Okay, that must have happened before I had that critical failure. Okay, I was going to show you the answer to that one, but don't have that.
For 13?
For 13, yeah, I didn't. It's not on this. It's not in the solutions. It's not there.
I did I can throw you the answer, and I mean, if you want it, I don't know if it's right, but I'll throw it to you.
Well, I can do it real quick because I'll cheat. I'll use the rules that we're not supposed to. I'm going to do that derivative, and I'm going to use a chain rule. So the derivative of that will be, okay, the outer function is the square root function. So the derivative of the square root of something is 1 over 2 times the square root of that something, and then times the derivative of what was under the root, which is just 1. So that's your derivative. And we want to plug 1 into it. So we plug 1 into that, we get 1 over 2, 1 plus that, that's square root of 9, that's 3. So you should get 1/6. That's your slope. And so your equation of your tangent line should be y minus 3 equals 1/6 x minus 1. The 1 and 3 came from here. So this is, again, this is not the work I want to see, but this is the answer. You have to get this, you have to be able to get this answer using the limit definition. Okay, that was the first part I wanted to clarify, is that I will expect that. And on the next problem, you'll see I did work this one out. Find the equation of the line which is tangent to this curve at this point. And I went through and worked out. I used this limit definition, but you could have used either one. You could have done it with the h goes to 0 or the x goes to a. You should get the same result. So that's the work for that, and here's the equation. Okay, that was the first review. The second review, I didn't get a chance to work these in class today. Where is it?
Sorry, we just popped through office hours to run them over then.
Well, let me see. Here they were. I asked you to look at the first four, right?
Yes, sir.
Okay, so I'll just tell you, kind of guide you through these. This first one, do not do the quotient rule. Okay, because you have a single term on the bottom and every term on the top is a power of X. So what you want to do is you want to split this into 4 different fractions. You want to put this over that, then this over that, and this over that, and this over that, and then mess with the exponents, get everything cleaned up, and then do power rule. I did one like that in class. The second one is a product rule. There's your product. Derivative of this times this plus derivative of this times this, you're done. This one is a quotient rule. Derivative of the top times the bottom minus derivative of the bottom times top over the bottom square. Number 4 is a quotient rule, but when you go to take the derivative of the top, there's a product there. No chain rule on this test, okay? But you can see if you were to scroll down and look at the rest of the problems, you can see that these start requiring chain rule. Okay, these are all in chain rule. Here's implicit, right? This is implicit differentiation. That's what we were covering today. More implicit, more implicit, more implicit, and then word problems. Okay. So the test, what you should expect is that we're going to come in at 1 o'clock on Thursday. Oh, I need to state, oh, it's not for this week. Never mind. It's the 8th. I'll just let y'all know now. On the 8th of July, we don't have a test on the 8th, do we? Please say we don't have a test on the 8th. Okay, good. We don't. On the 8th of July, I will not have office hours before class, just so you know, on the 8th of July. So we will come in on Thursday at 1 o'clock. Everyone will show up. You have to make sure that your camera can be placed in a position where I can see you and your entire workspace, right? And when we come in, I'm gonna email everybody the test. If you have a printer, you'll print it out. If you don't have a printer, you have to handwrite all the problems. As soon as you've printed it out or written them all down, you can start the test. And I'm probably just going to give you we'll probably take 10 to 15 minutes in the beginning just to get everything in order. And then I'll probably from there give everyone an hour and 40 minutes to do the test. And so it will be a timed test. And when the time's up, you'll have to submit the test through Dropbox, which I have not sent you the link to the Dropbox yet. I will. And then everyone will have like 10 minutes to upload their work to me through Dropbox. And then I will be coming back to Zoom and I will be continuing on implicit differentiation. Probably for 30, 45 minutes. It's probably all we'll have, but I am going to continue with it. Are there any questions on that?
Yeah.
I have a question.
Go ahead.
Alejandro, go ahead.
Yeah, I was just gonna ask that. I think you mentioned, earlier when you were talking about the test the other day, that could we use our formula charts if we wanted to?
Yes, you just have to have them printed out.
Okay.
Yeah. So the way that the way the camera is going to work is that, I think I've said this already. Your camera has to be in a position where I can see you in your whole work area. So like this right here, you see me? You don't see me? Stop sharing this. Okay, can you all see me? Like this is kind of what I'm looking for. Actually, I'd like to see a little bit more of what's in front of me here, but this would work, okay? What doesn't work is this, okay? Because I can't see what's in front of you. And so you're either gonna have to use a phone or you're gonna have to use, if you have a laptop, you can move it around. If you have a desktop, you can only use a phone, I think, unless you have a webcam you can move. So if anyone wants to show me what they plan on doing right now, that's fine. Like Alejandro, that's perfect. Yeah, do y'all see Alejandro? Let me see if I can do this. How do I do this? Spotlight for everyone. Can everyone see Alejandro? That's perfect. Okay. I can see what's in front. And how do I undo that? Shit. How do I unspotlight you? Right, there you are. There we go. Okay. So, you know, that's what I'm looking for. Any other questions?
Just as long as you can see in front of us and our desk, we're good. And
Yeah,
our
so
computer
like-
screens, I guess.
Yeah, like Cody, what you have now would not be okay, right?
Right. You can't see me in the
Yeah.
front.
Um,
I'd show you my angle, but my desk is a mess.
yeah, don't worry about it right now. I'm not asking. If you want to show me, you can, what you plan on doing. But it's an important part of the test. Because if you can't get your camera set up properly, I can't let you take the test. It's just not, I'm trying to be fair. I'm trying to make this a level playing field for everyone. And there will also be a point in time during the test when we first start where you're gonna have to show me, everything on your desk. So you're gonna have to like flip through each page on your desk and show me what's in front of you. And then you can start working.
So ideally, move everything that you don't need off the desk before the test.
I'll let you know when it's time for that. You know, when everyone's printing the test out and copying the test, that's like a free time. But there will be a point in time where I say, okay, that's it. Clear your areas, show me your stuff, start the test. You can take a restroom break, you know, one restroom break, 5 minutes. Don't disappear.
And then will we be all in one big room or will you split us up into breakout rooms? I don't.
One room.
Okay.
It'll be in one room and everyone will be muted. I don't mind if you listen to music. You just need to have the ability to hear me if for some reason I need to make an announcement. So if you want to have music on in the room, that's fine. No one's going to hear you. You want to have headphones on, just make sure you can at least hear me if something comes up.
I know you mentioned it on the first day, but really quick, what was the calculator that we're not allowed to use?
Anything that has CAS on it. So TI-89, which most people don't have TI-89s, but TI Inspire CAS. It has to say CAS on it.
Okay,
And I'm not
thank you.
sure that, you know, do you know what kind you have?
84
Yeah,
plus.
you're fine. Yeah, you're fine.
Yeah, the T1 Inspire it has like the CAS on the top, doesn't it? If you have it on there.
So that's okay. Yeah, that 36X Pro is fine. Jair, that's fine. Yeah, I mean, if your calculator was under $140, it's fine. It's the higher end ones that are really expensive. That
Random question, but is that an aquarium or a terrarium behind you?
it's my daughter's aquarium. We're down to one fish.
Okay.
I'm not saying I want it to die, but we're down.
There's
to
heavy
one,
implications.
we're down to one fish. You know, I
I
don't
was
want to
just
just get
curious.
rid of it.
Yeah.
you
I
know.
was just curious. I'm a snake guy, so I got snakes in terrariums and stuff. So I
Yeah.
feel
No,
out.
it's just a little aquarium. The only fish left is that one, the little sucker fish that goes along the bottom. Those don't die though. They just keep going and going. All right, what else? Formula sheets, make sure they're printed. Blank paper, you're not going to be able to write out of a spiral or notebook. Because then I don't know if you're flipping around looking at notes or, you know, a copy of the review or, you know, so blank paper, torn out of a spiral.
Oh yeah, so when we're done with the tests, do we like message you through Zoom that we're done, then send our
Yep.
photos to the Dropbox?
Yep, you'll send me a chat, say I'm done, then you can leave and you'll have like 10 minutes, 15 maybe, for you to upload all your work. And then I'll let everyone know like what time I'm gonna resume class. When we start the test, I'll say, okay, everyone, the test is gonna go till this time, then I'm gonna give everyone 10 minutes after that to submit their work, and then I'll resume class at this time, whatever it is. And so you can, if you finish in 30 minutes, 45 minutes, you can leave and come back later. And, you know, if you don't come back, you don't come back. I'm not, whatever we do.
More or less.
What's that?
More or less. Do you know how many questions there are going to be?
It'll
on
be
the
very
test?
similar to the review, maybe not quite as many as the review. I try and make it where you could work through it in an hour, 40 minutes. And when I say you, I mean, I normally make the test, take the test and time myself, and then multiply that times 5 and hope that that's under 100 minutes.
Okay,
So,
okay.
Yeah, so if I can do it in 20 minutes, I expect you can do it in 100 minutes.
Sure, thank you.
And that's the hard part, because everybody's different. And, you know, that's one of the challenges, you know, one of the things that's, I think this is important. Some people don't, but I think this is a huge factor. It's not just can you do calculus, it's can you do it efficiently, right? So like if I gave you a chain rule problem, you know, like one of the ones we did today, and you work on it for 2 hours and you get it, like, okay, great, you got it, right? But if the problem really should only take, if it only takes me like a minute, then at most it should take you 15 minutes. You know, like there is part of this is gauging your ability to do it efficiently and quickly. Because just like an employer, right? Like efficiency is part of what employers are looking for. It's not just can you eventually get it done. They got to pay you, right? So.
Well, we won't submit the Canvas. It'll be another drop link, right? And you'll send that in the original email, I guess.
I'll probably send that the day of the exam.
And then single PDF upload.
Yep, single PDF, that's important. For this first test, I might let it slide. You know, if you send me like 13 JPEGs, I'll get all pissed off and I'll email you and be mad at you. But as long as you get to me on time, I'll be happy. But on the, you know, on the next exam, no. Like, you know, I've given everyone an opportunity to practice that if they want. So those who've tried it have, and those who haven't. So everyone did it for the quiz, right? For the quiz, you had to do it. So if you did it, so.
Quick question. You said ones that, okay, because I have a couple of calculators here. I'll just see, make sure which one that needed. So you said it has an S on it. What is it? Because I have this. Oh, okay. So I couldn't use the whatever. Okay, so I can't use that one.
This one.
Wait, no, did that say
Okay,
CMS?
so I can use. It was this one.
Yeah.
Yeah, so the CX, yeah, this one.
Hold on. I need a spot
Or
where
if it,
oh no, CX is okay. CAS.
CAS,
Oh,
okay. Because I have a bunch of different ones. I was just
I know.
making sure that it wasn't
Both
like.
of the ones that you've shown me there are okay.
Or then, it's just a cheaper one. So I
Let
was
me
just
do
like,
it this way.
so I can. So this one will.
Yeah, I didn't see that one, but.
All right, this is the first one, but yeah.
Yeah.
The CX.
So, can you all see my screen again? By the way, if you need to go, you can go. I mean, we're done time-wise. TI Inspire CAS.
I was pretty sure that the CX was the CAS model for that.
You
the
where it says
Inspires.
CAS in the corner?
Yeah.
Yes, that you cannot have.
Okay. Yeah, it doesn't have that on there at all.
Fair
I
play.
mean, it's. I
What
mean,
does it
if
actually
you have
do?
CAS, you still have to know how to use the calculator to do what you're not allowed to do, which there's a
Yeah.
learning curve to that also, you know. But still, just again, it's about a fair playing field here, you know, I don't want someone to have a calculator that can do derivatives and other people don't, and it's just about being fair. That's the only one I know of other than the TI-89, which is what I have.
The CIS, is it just like calculus functions for a calculator or?
CAS stands for Computer Algebra System.
Okay, so it's just all the advanced algebra jazz and all that.
Yeah, like, let me see.
Yeah, because I have a TI-89 as well, but it's a no-go.
Oh, you have a TI-89?
I have the TI-89 and then also the TI Inspire base model. So I just,
Okay, so
I
here, I'll
mean,
try and show this on my, I don't know if this will show up. That might help. I don't know if that's gonna work. No, that's not working, is it?
mm-mm.
Yeah, that's not working, but basically I just took the derivative of something on here and it gave me the answer. So,
So, well, like you really like, so if I go to Cal 2, will I be able to use like my TI-89 in Cal 2, or is that like, is that just gonna be something like I just shouldn't even get used to using at all?
well, I think that you could use it in Cal 2 to check your work, but it would never be okay on a test because you have to show your work in order to get credit. Same with this test. Even if you had a CAS system, you still have to show your work. So,
Well, like even if we know the rules, you still want us to show you like the physical method with the limit definitions. So something similar.
I
to that, I
wouldn't
guess.
get rid of it. The TI-89, this is like my favorite calculator. It's probably like the fourth one I've owned because I've lost them or they've been destroyed or something. This
Yeah,
is
I'm
like,
holding on to mine. It's
this is the holy grail of the brains of this calculator are the same as the Nspire. The Nspire just has a different operating system. It's more user friendly, I guess, colors and pretty things, but it's still the same like built-in functions.
I think I found a solution to the CAS calculator because that's the one I have.
Yes.
But I went to settings and I don't know if you can see it, probably not, but it says CAS mode. And I went to it and you can actually turn it off.
Okay.
But I don't know if you would still not want me to use it. I can turn it
Well,
off.
Do you have another one or no?
No, this is the only one I have. The reason I got it is because my high school teacher recommended it to us, so we just bought it. But yeah.
Yeah, so like in high school, a lot of what's happening in high school is that they're basically using the technology to do the problems.
Yeah.
In the calculus, the mechanical part of calculus is kind of like just being left to the computer,
Yeah.
which, you know, that's you can do more advanced problems that way if you can rely on the calculator, which is, I can see pros and cons to both ways, but normally university calculus is very much about the mechanics. And again, it's not about the mechanic. It's not about you learning how to take derivatives, and it's not about you learning how to do all the things that you're going to do in calculus. It's about the critical thinking that's involved. Like today, the chain rule. I mean, there's critical thinking involved in that. And so to just type something into the computer and then just be like, oh, there's the answer, write it down. You really don't, you're not using that part of your brain that has to like think, you know? So at the end of the day, the degree that you get is less about the knowledge as much as it's about your ability to think critically and problem solve.
Yeah.
That's what it's about. So calculus really, Cal 2 really gets you to think that way.
Yeah.
So, okay, so for you, what I will say is that if you can't get your hands on another calculator, then you can chat with me during the test, say, hey, you know, I'm going to disable this feature and
Yeah.
whatever, and then I'll have to see your work. I don't want you to have to buy a whole calculator because of it, you know.
And I probably won't even use it that much.
Yeah, there's not a lot in this
Yeah.
test that's going to require a calculator.
Yeah, because I haven't really used it that much on the homework anyways. Like even if I do use it, I'll just have it off just in case.
Yeah.
Hey, sir, I was just thinking about it. If I show you this setup, I don't know, it's just in case my internet is still killing me later on Thursday as well. So I was just told a message, but I got something like this, my table, everything in front of me. I mean,
good.
okay, I got a backup at least, that's good.
Yeah.
Oh, goodness.
I had this guy last semester, I swear, he had like a really small, it was almost like a TV tray dinner, like a TV dinner tray, like what are those? You
Like
know what I'm
this?
talking about. Yeah, like that. And I swear this room he was in was like 30 feet by 30 feet. It looked like a prison cell. And he was like on an aluminum chair, sitting in the middle of this room with this little table. And he just looked like he was being tortured or something. It was hilarious. I was okay with it, but it was so funny to see him there in the middle of the room.
I must say, it's not as bad too. Like when I had been signing up for your course, when I was looking up while they rate my professor and everything, I saw a few comments about the test taking and how you were apparently extremely OCD about the camera angle and everything, but it doesn't really seem that bad to me if you just set it up right, so.
Well, I think those are the people who would like for me to not care about their camera angle.
I guess so. I don't know.
I had students that I'd had to basically drop from the class because they refused to put their camera in a position where I could see in front of them. And I had one student who actually finally did put their camera the way I wanted, and they turned in a completely blank exam. So, you know, and like I said, it's about fairness. It's not about me trying to be an asshole. I mean, it's about fairness. I know a lot of you in here want to learn and you want this test to be a gauge of what you know, and you want to see where you are relative to the rest of the class. And when you have this, when there's no sort of rules, then all the grades don't mean a lot, because you've got serious students who want to learn who may get a C on the test, and you've got someone who sat there with a laptop open doing Wolfram Alpha the whole time or whatever it is. And you know, it's just one of the downfalls to doing Zoom. But yeah,
right, with that, and then like I know there was one guy in one of my math classes. I don't know if it was my 1314 or my 1414, but or sorry, my 1414 or my 2412. But I know he had dual monitors, and I know I could never pinpoint when, but I know for a fact that during the test he's looking at the camera here, and I know that the other monitor's on with the stuff, because we would do breakout rooms a lot, and every time we got in there, it was like he'd never been in the class one day. He had no idea about anything. So, it was just like, man, I mean, I get you want to do well to an extent, but I mean, there's a way to go about it, you know?
I had a guy last semester on camera who didn't realize that his camera was a wider field of view than he thought. And so he was sitting there kind of like this, and he had a mouse, and he was underneath here like clicking, and I could see him looking like pretty far away from him. And he would be like clicking and looking, and then he'd be doing that for like 10 minutes, and then he'd come back and start writing things down, and he'd be looking up, writing things down. And it was just so obvious.
That's the other thing.
You know?
It's like, if you're gonna do it, at least try to put some effort into it. I mean, man, some of these people, like there was in my 1414, I know we had like a group chat set up, something similar. We have like a group me for this class, but it's just for review and stuff. First test, there's someone sending me messages about, sending the group at least messages about, you know, work and things like that. And it puts me in a hard spot, because I don't know, do I turn them in and then make myself like the bad guy, or do I just be quiet about it and let them fail on their own, you know, like, cause then like, I don't want to be like that asshole, you know, that turns the whole class against me, but I also don't want to feel like it's, you know, an unfair playing field. So that's a struggle I have.
You know, I had a situation in college. I'll never forget this. It was a class called Abstract Algebra, and it's like a junior level math class. And we were in this huge auditorium. There's like 200 seats in the room, but there was only like 18 students in the class. So we each like had, you know, it's an auditorium, so we each would have an entire row, like a movie theater. We just had so much space between us. And during the test, this guy who was sitting in front of me, like 5 rows in front of me, he had every single, he had like 5 textbooks opened on the ground. And he was just like thumbing through the textbooks during the entire test. And so I didn't turn him into the teacher or anything like that. But after class, I went up to him and I asked him what his major was. And he said it was math. And I said, well, I better not see you in another math class. Because, you know, I saw what you did during that test, and if you can't do this work, then, you know, you're wasting your time.
I
I
just-
never saw him again. I think it's one of those things where it's like, you know, it's about integrity, right? I mean, that's what it comes down to. I mean, you either have it or don't, you know, so. I can put all these safeguards in place. People are gonna find ways to cheat. We had a guy a student, who made a video of themselves doing a test. And then during the test, they put their webcam pointed to the screen of their own video. You know what I'm
Yeah.
saying? So
Just
it was
the
like,
ingenuity there.
I mean,
They could have
that's
done the work
pretty
if they
clever,
wanted
you know?
to.
Yeah, I know. They would have taken the same amount of time to study, you know? I mean, there's ways to get it, but so my workaround for that is that during the test, like at random moments in time, I ask everyone to write a word down on their test and show it to the camera. So that way, you know, I have documentation that you were taking that test, and when you showed the camera that work, it was your work and it was the word that I told you to write on top of it. And I mean, the thing is, I'm not that anal about it. It's only if I feel like something's going wrong that I do something like that.
Yeah. I mean, I feel you. I mean, even like outside of math classes, my first history class, she says no notes on the test, and you can hear people thumbing through the pages of their notes as we're testing. And it's like, at least mute your mic, guys. I mean, it's